and I'll let you lead in, Michael, when you're ready.
Yeah, I'm watching the YouTube stream on my side monitor. Let me make sure it's going live first, and then we can get
Yep.
going. All right, looks like it's on. All right, well, welcome everyone to day 2 of the 3rd annual Reddit Robotics Conference. We are super excited to have you all here with us today. We have some great keynotes coming up. We have some wonderful community presentations, and we're going to start off our autonomous mobile robots section with Scythe Robotics and their CEO and founder, Jack Morrison. Scythe Robotics is a company that is building mobile autonomous robots to help do landscaping and lawn mowing. So with that, Jack, please take it away.
Awesome. Well, thanks, everybody. Good morning, Reddit, our robotics community. Great to be here. I'm Jack Morrison, co-founder and CEO of Scythe Robotics, based here outside Boulder, Colorado. Really excited to share what we've been up to. And I'm going to be using Scythe as sort of a way of talking about more general things for taking autonomy off-road. So that includes things like durability and testing and sensor selection. So we'll get into that here in just a second. All right, just getting my Zoom all fully configured. All right. So a little bit about Scythe before we get into the robot part. We consider ourselves at Scythe a team of environmental innovators who strongly believe that nature and technology do not have to be at odds, but rather that we can use technology to better care for the planet. We think that autonomy holds this tremendous power to transform how we care for all of our outdoor spaces, and all the Scythers on the team, from our hardware and software engineers to the test squad and customer teams, are really helping to make this vision a reality. We think, we're builders by nature, and we are building for nature. We want to help humanity take, an order of magnitude better care of this beautiful blue and green marble that we all reside on together. Now, we're pioneering these solutions to more sustainably care for all of our outdoor spaces and help the businesses that do that work grow, because it's commercial landscapers who ultimately are the ones cultivating and maintaining all of our most frequented outdoor spaces, from parks and campuses to sports fields and schools, housing developments and apartment complexes. And that's really where we spend a lot of our time outside. And it's landscapers who sit at the forefront of this green space management, which is why we're focusing our initial efforts on solutions that can really multiply their impact and grow their businesses, so that more people will go into this industry, so that this industry can do more with the people that it can attract today, and just make this a greener, healthier world. There's so many benefits to increased levels of green space. Studies have shown lower drug usage, like prescribed drug usage, better mental health, better physical health for folks who live near green spaces. And we want to help landscapers and communities to cultivate more of that green space by making it radically easier to take care of all of that space. And just a quick aside about the landscaping industry, because it's not one that many people know all that much about. It is actually a huge market. The US landscaping industry is about half the global, I know we've got a global audience here, about half of the global landscaping services market. We really love our grass and our domesticated outdoor spaces here in the US. So it's a $176 billion services industry. That means all of the work going into caring for these spaces. There are over 5,000 businesses in the US in the landscaping industry who do more than $1 million in annual revenue every year. So that's a lot of folks going out there taking care of these spaces. And all of those companies employ well over 1 million workers, and yet that's still not enough. There's about 40 million acres of turf grass in this country. It's about 1.9, about 2% of the entire lower 48 in the US is grass that needs to get mowed, every week or two throughout most of the year to keep it at a length that's enjoyable by folks out there. And to maintain all of that, there's over 300,000 commercial mowers sold annually. And we'll talk about why there are quite so many sold every year, why they don't just last a little bit longer. But it's a lot of mowers and a lot of equipment that goes into caring for all of this. And the landscaping industry, or as they prefer to be known, the green industry, is really the one industry tasked with just caring for the planet. They're not really extracting anything out of these outdoor spaces, unlike ag or mining. They are just there to cultivate green space and to help it be healthy. But industry OEMs really haven't kept up with the technology that these landscapers could use for decades. Mowers today look almost identical to mowers 30, 40 years ago. There are no new emissions controls, no new digital technology on them. They are basically just a gas engine strapped to some belts and pulleys and a hydraulic system that powers turning tall grass into short grass in a really noisy, inefficient, and polluting kind of way. But landscaper contractors are suffering an incredible labor crisis that technology just has not yet been able to help them. Over 3/4 of them say that their growth has been stunted by a lack of labor. And that's huge because landscaping is an incredibly low margin business, and they need to grow their businesses to take more money home as owners at the end of the day. And they really can't do that because they can't find the people to take on new jobs. And this has been happening for a decade plus, well before COVID exacerbated, immigration challenges in the U.S. and created worker shortages. Contractors are also facing this urgent need to transition to more sustainable operations. Property owners and regulators are requesting this, but the industry just hasn't kept up with giving them equipment that allows them to do this. A little stat for those of you who are interested in the climate fight, commercial mowers alone, just commercial mowers, so that's these larger spaces, not single family home mowers owned by, consumers, emit more than 40 million metric tons of CO2 equivalent gases annually. That's equivalent to all of the fuel use in agriculture to, harvest and care for all of the crops and the cattle and livestock that agriculture produces. It's equivalent just in landscaping, just in commercial mowing. So that's a huge amount of pollution. And that's not I'm talking about the volatile organic compounds, the VOCs, the NOx, all of these other polluting gases that really harm air quality in the areas we live. And so it's really the convergence of these two big trends, sustainability and this labor crisis, and then the availability that I'm sure everybody here is well aware of these autonomy supporting technologies like high performance embedded compute, new affordable sensors, new software techniques that has made this the perfect moment for us to tackle challenges in the landscaping industry. And we think upend the outdoor power equipment status quo by bringing autonomy off-road. Okay, that's enough about us and about landscaping. I'm sure everybody doesn't need to learn any more about that for a little while. Let's get into some robots. So while the landscape industry presents this huge opportunity for autonomous solutions, it obviously introduces some challenges around being autonomous in outdoor, off-road, unstructured environments. These are some challenges that are really different from those with indoor mobile robots or autonomous on-road vehicles. And I think easier in some ways and more challenging in other ways, but ultimately ones we're really excited about. And I'm going to use Scythe and M.52, our autonomous electric commercial mower, as the example here. But I think I want this to be sort of a conversation about more broadly how we take more robots off-road and how we think about bringing autonomy to all of these other industries that don't fit nicely into some of the boxes we've seen robots in so far. So let me start by introducing you to M.52. Designed in-house and built from the ground up, M.52 is specifically capable of helping commercial landscapers who maintain these incredibly frequently visited outdoor spaces like parks, HOAs, fields, schools, to get more done with the crews that they already have. It looks a lot like any other stand-on commercial mower that folks, especially here in the US, may have seen cruising around their housing development or their office park, their schools. It's got a 52-inch mowing deck on it, kind of the workhorse size machine in the US. It's applicable to a broad set of use cases from fields to apartment complexes, backyards, all of these different areas, can mow well over 8 hours on a single overnight charge, and has this design that, like I said, is familiar to landscapers. They know how to hop right on it and start mowing manually or autonomously with really simple, sort of intuitive user interface. Now, M.52, of course, the big value here is it mowing on its own. And it uses a combination of computer vision, machine learning, and a whole bunch of robotics approaches to identify and navigate around obstacles, to plan its path around a mowing area, and to help these landscapers not have to think about mowing while they go do the rest of the work on a given property. It'll stop for people and pets, but go around trees and poles, enabling these landscapers to just get more done. And that's really what it comes down to. Our job is to help landscapers save time. We want M.52 to take care of the mowing so that the crews are freed up to perform the more complex, higher value tasks on site. That's like edging, trimming, picking up trash, planting flowers, dealing with the hedges. These are all the things that make a property shine and really allow landscapers to show off their abilities and do the more human part of the job of crafting a great space rather than just turning tall grass into short grass. Mowing is boring, frankly. We should have robots do it instead. And the last thing M.52 is able to do is leverage the data that it collects, right? It's got cameras that are constantly recording imagery from the spaces, sensors that know where it was and how long it spent there. And it can leverage all of those insights automatically to help landscapers optimize their operations and their performance to get more done. Because ultimately, the robot is just a tool to help a business do more. And we want to leverage all of the abilities of this tool, of this robot, to help that happen. Now, I'm going to skip to a little video to introduce M.52 because robot videos are way more interesting than me talking, and then we'll get back into it after this.
Say hello to the next generation of mowing built by Scythe. Say hello to M.52, the industry's most advanced autonomous commercial mower. M.52 is smarter than ever. An improved sensor suite and advanced AI allow it to see and perform like a human operator. Now your crew can finally focus on the higher value tasks that leave properties looking their best.
It's important for us to stay innovative because it gives us a chance to really maximize what we're able to do on a property to help with the efficiency and the quality of work that we can give our clients, along with maximizing the volume that we can handle in a day. M.52 navigates complex properties like a seasoned pro. It handles contours, tackles slopes, and automatically adjusts mow patterns to deliver your customers a cut above the rest. An all-electric drivetrain keeps it out of the shop and in the field. No fuel, no maintenance, no downtime.
Using Scythe robotic mowers is allowing us to do more volume of properties because our guys can finish the detailed work a lot faster and move to another property.
This new era of mowing means doing more with the crew you've got. It means all-day power without pollution. And above all, it means a perfect cut every time. Mow more with the next generation of Scythe.
All right, so there we have it. That is M.52, the lightning introduction to it. The last piece I wanted to say before we get into the tech part is that, again, the point of building a robot is to get lots of them out there and to help do more. And to do that, you have to take into account how you bill for the robot. Selling a multi-$100,000 autonomous mower wouldn't be very useful because not many landscapers could afford that. And so when we talked to a lot of landscapers and, heard about how they felt about their mowers, one of the things we heard over and over again was that they were sick of paying to fix machines that would just keep breaking and tired of becoming what they called iron collectors instead of focusing on their real work. They end up with these scrap heaps filled with mowers, parts of mowers and entire mowers after only a couple of years because these existing gas mowers break down so much. And, it occurred to us that all of these innovations in M.52 also unlock a better way to bill. We heard what our customers' pain points were, and we turned the industry's traditional, and we feel strongly misaligned parts and service model inside out. So instead of charging customers when a machine breaks, every time the belt breaks, they need a replacement one, or the engine needs an overhaul, instead of charging them for that, we bill based on the work that's actually getting done out in the field. So for every acre that M.52 mows autonomously for a customer, we aggregate all of those over the course of a couple of weeks, and then we bill based on how many acres the machine mows. And that actually builds a much deeper, trusting relationship that's vital for introducing something new and innovative into a word-of-mouth legacy industry like landscaping. Okay, so to build a machine that can stand up to the demands of commercial mowing and, of course, the high expectations of our customers, we had to design for a few really critical considerations and constraints that these robots will face in unstructured outdoor environments. This includes things like the durability that influence, or the durability demands that influence our hardware design decisions, the dynamic and dirty environment that we're working in these outdoor off-road spaces that influences sensor choices and our strategy for perception development, the power limitations and the environment we're working in had a big influence on our approach to computation, from the processors and the boards that we actually use in the machines to the programming language that we use to develop the software running on all those computers. So we'll kick it off with durability. The challenge here is that off-road robots have to be rugged enough to stand up to both their outdoor environments and the tasks that they're doing. They face things like tough terrain and steep slopes, really intense and variable weather, and just stress of daily operations and being a machine that's not only driving itself autonomously, where we have a little bit of an ability to, be gentler with the machine and optimize for the lifetime of it, but also manual operations. Landscapers are not kind to their equipment. They've got a job to get done, and they don't really care if the machine can't hold up to it. They've got to go fast and get it done. These machines, basically in landscaping and in other off-road environments, face things like uneven land, hidden rocks, even different types of grass that can wear on machines differently. Sandier soils will wear down mowing decks really quickly, for instance. Incredibly hot sun out there, 100+ degree Fahrenheit temps, over 40 degrees in Celsius. Unexpected downpours that will flood everything around it, tons of mud. They've got to get on and off trailers repeatedly, up and over curbs, and then all around the properties that they're operating on. Now, of course, this isn't exclusive to autonomous machines. This is something that the existing gas mowers have to deal with as well. And they just don't really do all that well, frankly. Sort of surprising to us. A commercial mower, for context, can cost up to $25,000 off the lot. They only last a couple of years, maybe 3 years max, 2,500 hours of runtime. Because they have so many different moving parts. We've counted hundreds of moving parts in a single gas mower, from all of the components of the engine to the power distribution system, like the hydraulics, the belts and pulleys, and all of those pieces need preventative maintenance, can fail over time. And then, the last part of it is that the manufacturers and the dealers actually benefit when these machines break, because that's what brings customers back to them to spend more money. And so there's very little incentive to, actually improve the durability of these machines. And that felt wrong to us. And so again, we wanted to change that. Going electric is one way that we have completely flipped the game here. We've got about 1/10 the moving parts. We've got 3 blade motors, 2 deck motors, and then the deck goes up and down. And that's about all of the moving parts, along with the casters on our machine. Almost none of that needs ongoing maintenance. We've seen in the automotive space how incredibly robust and durable and maintenance-free EVs can be. I've got an electric vehicle. I think I've taken it to the shop once in 3 years. It's pretty incredible compared to the gas car I had that had to go in every 6 months, probably. And so just going electric allows us to avoid a whole bunch of the durability problems that would slow down our robots, keep them out of the field, and make it harder for our customers to get more done. Now, this isn't, of course, possible in every autonomous off-road application, since there are many that need all of the gas, all of the power and the lifetime that a gas engine can bring in terms of just being able to quickly refuel. But it's something I'd strongly suggest folks consider as you look at taking an autonomous solution off-road, because the durability is so much better. And then there's this climate angle of just being better for the earth. If we're building these machines to do things off-road and to exist out in the field, we want to help be good stewards of that space, and eliminating emissions is a great start to that. Cool. And then to ensure that we really deliver this durability that our customers demand, we've engineered our machine for extreme outdoor conditions that off-road robots face, by designing it in-house from the ground up for autonomy and manual operation, where we can reinforce the protections around these sensors, like really thick Gorilla Glass around the cameras, a really rigid structure to keep the cameras in calibration, choosing sensors that are designed themselves, like our ultrasonic sensors around the base. They're designed to be in these outdoor environments. We use what we consider commercial grade materials, really thick steel that can last through all of these environments. And then, we want to build a machine, and we test that the machine can do its autonomy and its manual abilities across all sorts of terrain that our customers might encounter. And of course, when you're considering durability out in the field, testing is a critical part of maximizing that ruggedness for any off-road robot. In order to build a machine that before we fielded it was ready for the rigors of commercial landscaping, we've put it through some pretty extreme environmental testing to ensure it will stand up to the task at hand. This includes, extreme terrain testing, accelerated lifetime testing, thermal and environmental testing, like soaking these machines to make sure that they really are water resistant, and then pointed tests to look at individual possible points of failure on the machine and make sure that we've covered them to the extent that we expect them to see anything out in the field. We've made some design choices early on, built on best practices to help these machines from the time they're built survive out there, meeting IP66 standards to prevent dust and water ingress, using networking standards inside the machine for data transmission, like for the cameras, FPD link or GMSL instead of USB or Ethernet. These are automotive grade camera streaming protocols that rely on really well-tested coaxial cables and are incredibly robust to noise and to all of the sorts of things that happen in an industrial machine. And then relying on CAN primarily for intra-bot networking. So between all of the various compute boards that are within this machine, we've got them all wired up over twisted pair CAN, because that is, again, an incredibly robust way of communicating within a machine like this. And actually, we ended up building our own CAN open source library called Confetti to help send data across that CAN network because we didn't see anything that really met our needs for seamless integration with CAN Open. So we can talk about that a little bit more later, and you can check that out on GitHub. We're really proud about our first release. All right, so the second consideration I've got here is around sensor selection and perception strategy in these unstructured outdoor off-road environments. Of course, your machine has to be able to understand what's around it and do that really robustly to operate safely in off-road environments. And the challenge is that outdoor environments are not sitting still. They're dynamic, they're dirty. Nature's always changing. The trees are growing, the branches are waving, leaves fall, colors transition, water shows up, and then sometimes it goes away. And we need sensors that work in all of these possible operating conditions, including those with pretty stark lighting differences, dusty or grass-filled air, and abundant dynamic obstacles. So to perform in these conditions, our real-time live perception is a must-have, right? You can't offload this compute to the cloud because you'll never have a reliable and timely enough connection to do this. So all of our compute runs on the bots online, and things like persistent pre-mapping, like what's often used for autonomous on-road vehicles, just isn't nearly as effective because these outdoor landscapes are always changing. It's not like we have static buildings that we can map against. Trees are being trimmed, especially in landscaping. Trees are being trimmed, branches are growing, leaves are falling. All of these things that mean we need to deal in the perception domain with changing things as they come up. And the ruggedness of the environment also has to inform our sensor selection. They've got to work in this range of operating conditions and detect things like fouled sensors, like a mud-covered camera, on their own. On the plus side, though, off-road, we're generally operating at much slower speeds. And this is, I think, a key thing for me that made building an off-road robot a really exciting opportunity is there's all of these ways that the operating domain is actually reeled in a whole bunch. We're going at tops about 8 miles an hour with M.52, which is a far cry from even the slower city driving speeds. Then off-road generally has the benefit of the doubt that you can just stop if something doesn't match your expectations, unlike in on-road environments where you'd probably get rear-ended if you slammed on the brakes at any point. And so that's a key thing to sort of keep in mind is if you come from the on-road AV space or the indoor mobile robotics space, the different requirements and constraints force some different possibly decisions around what we use for our perception. Now, we found computer vision to be the most productive and beneficial approach for perception on M.52. But we considered others. We've got 8 high dynamic range cameras on this machine. It performs really well for us because it can be really resistant or robust to fouling, like dust in the air, dirt flying around us, grass getting clipped, and from a cost perspective is much more appropriate for the sort of type of machine we're building. This is not something we want to cost hundreds of thousands of dollars to build. And even the cheapest LiDARs today can be $10,000 plus for really the rich sort of geometric information you want from an autonomous mobile robot. Whereas our cameras cost a fraction of that for all of them combined, provide us not only structural data through geometric computer vision methods, but also with that rich RGB information that can feed into all of our semantic perception abilities. And you can't just take any old cameras off the shelf. In indoor environments, a 60 decibel dynamic range is typically okay. You have, usually pretty uniform lighting. But if you think about being off-road and out in a, tree-filled area, you can have really stark lighting differences where you've got shadows that are incredibly dark, and then you're staring simultaneously right into the bright sun. That means you need incredibly high dynamic range cameras. Instead of 60 decibel dynamic ranges, our cameras have 100, 120 decibel possible dynamic ranges, which allows us to resolve objects both in that sunlight and in that dark area simultaneously. Calibration is also a critical step, and building them really rigidly into the machine is something you have to take into account, because these are machines that get multi-G impacts on them out in the field, bouncing up and down, jumping off trailers or curbs. They can really get hit pretty hard, and so you have to design that in from the get-go. And then we've also got our ultrasonic sensors around the base of the machine. These are automotive grade, weather sealed ultrasonic sensors that work together to do really advanced things like multi-echo, cross-echo sensing, to give us not only a distance out away from the machine, but to some degree sort of a heading to that detection as well. These are tried and true sensors that are really proven to work in fouled conditions, like getting covered in mud. And so they're much lower on the machine where they do get covered in mud sometimes. And that can still, they can still work through that. Whereas the cameras, I think, and this is a key part too, is making sure your sensors are placed in a location where they won't most likely get fouled. Our machine's cameras are about 3.5 feet off the ground. And we found that to be a great height for them to stay out of the dust and the dirt and the grime that covers large swaths of the rest of the machine. And finally, we've got a bump sensor on the front of the machine as an absolute fail-safe in case something manages to sneak up on us and get in front of the machine while it's driving. And you'll note the two sensors that are commonly used indoor that we don't have on here, indoor or on road, are LiDAR, largely because it just doesn't meet that requirement that it can work in these fouled or semi-fouled environments. You get false returns on dust clouds coming up around it. It can be really difficult to do that. And again, it's just incredibly expensive. But I've seen it break multiple off-road robots because people didn't take into account how dirty that environment really was. The other one's structured light. That's like your old school Connect, where it projects a pattern and then detects that pattern. Unfortunately, those patterns are usually infrared light, and it turns out the sun is a massive emitter of infrared light, and so that structured light won't work very well in these outdoor environments. You can use IR cameras and do stereo from that, but again, we use the RGB cameras because they give us not only the geometric information that LiDAR or depth sensors would, but also, like we'll get into now, this rich ability to do semantic perception. So computer vision provides us all of these amazing semantics to differentiate from, our engineer Nick from the tree that he's standing next to, even if they're shaped kind of similarly. And we take a bit of a kitchen sink approach at Scythe to leverage both geometric and semantic computer vision powered by machine learning, because we need to have a redundant and a reliable perception system on the robot. So we detect obstacles both based on geometric cues, like there's just a blob in front of me, and on semantic clues, like if you can tell that's a dog, even if the shape kind of blends into the surrounding geometric texture around it. That's really critical for us to stay safe to anything that might pop up around us. And then finally, we've actually built all of this ourselves instead of taking off-the-shelf approaches. And I think this is actually a key part of building a really reliable off-road robot, because there are so many different pieces that need to run, and they share a lot of common bits from vision processing and the cameras that bring them in, that it's hard to plug together off-the-shelf pieces. I think at least today, with the technology that's available, hard to plug together all these off-the-shelf pieces and get something that really works cohesively together. These loosely coupled pieces either have massive redundancy in computing, say, key points across them, or force you to add a whole bunch of redundant sensors, like multiple RGB cameras that are looking the same direction, because they all have to feed into their own areas. And of course, the last bit is that the more sensors you add on here, if you've got, dedicated tracking, positional tracking sensors versus obstacle tracking sensors, that all has to feed into something that's doing the actual compute. And that compute power is pretty limited because of some of the demands around power budgets. We'll talk about this now. So we really had to tailor everything about our software processing to the task at hand. Not only the compute boards that we're using, the actual embedded computers, but also the software to keep in mind the limits to the power that we've got, right? These off-road applications can take an incredible amount of power to do the actual task at hand. If you're if you're an indoor mobile robot, your power consumption is actually pretty light. You're on a relatively smooth floor. You're sort of moving yourself around, maybe operating a small robot arm if you're a mobile robot. But there's not a whole bunch of resistance to what you're doing. When you're off-road, if you're doing things like cutting thick grass or harvesting or trenching or bulldozing, that uses an incredible amount of power just to do the task, not let alone to actually compute all of the autonomy abilities that you have to enable doing that task. There's also often a limited ability to charge nearby when you're off-road. Of course, there aren't outlets everywhere in a field. You can't sort of run a cable to it or do DC fast charge in the middle of a soccer field. And so that can be really challenging for emissions-free, fully electric machines to both be able to do the task at hand, do it all day and meet their customers' needs while also being autonomous. And so instead of packing some beefy desktop computers, off-road robots often need to make do with substantially lower power devices. For a little context, our machines, while they're out mowing, use somewhere between 1 and 3 kilowatts continuously. I know that's a wide range, but can really depend on what the terrain is you're looking to work in, how thick the grass is. But ultimately, that doesn't matter to our customers who just need a machine that works 8+ hours of mowing every single day. So we've really got to be considerate in the sensors, in the compute that we choose to meet that budget. And a desktop PC can draw upwards of 1 kilowatt on its own, which just from a power perspective would cut down our battery life by approximately 1/3 or more. And that's just not acceptable. We need to have an absolutely enormous battery. We've already got over 20 kilowatt hours of battery on board. And so to add another 1/3 of that would make an unacceptably heavy and large machine or give us an unacceptably low runtime. The other part about a desktop PC that anybody who's got a nice gaming rig at home will know is those things put off a lot of heat. That kilowatt of power that they're using is almost entirely going straight into heat waste that has to go somewhere. And in an off-road robot that's already trying to work in 100-degree temperatures and keep its batteries at a reasonable temperature, keep all of its compute from literally melting, that's a real challenge. And so what we did was we instead went with the pretty incredible NVIDIA Jetson platform, which has upwards of max 50 watts of peak power usage, has an incredible CUDA-capable GPU that has shared memory to the CPU to enable really efficient, mixed sort of CPU, GPU loads. And then also has all of these diverse sensor inputs on board. So it can connect directly to multiple CAN buses, to these automotive grade camera cables like FPD-Link and GMSL that I talked about before. It's even got a built-in microcontroller for handling real-time operations like timestamping your IMU data or doing really low latency computations. It's an incredible piece of hardware with a really small power budget and allows us to free up all of that power for other operations. Now, of course, it's not as powerful as a 4090. I never would never think to say that. 4090 and some of these desktop class GPUs are unbelievable and have so much power to them, compute power. And so we do have to be really selective in how we build our software to enable it to fit in that much smaller yet very capable compute budget. And the first choice you have to make as somebody building software is what kind of language do I use to actually develop that software in? C++ and Python are the typical robotics ones, often because of ROS integration. Python's super easy to work with, but it's way too slow for real-time processing on a embedded computer like the Jetson for at least most of the sort of low-level, high-complexity tasks. And then C++, very fast. I was a C++ developer for years. You can make great software, but it's just unbelievably unsafe. I've seen the same bugs in C++ code bases for years, and debugging a seg fault on a robot out in the field when it's incredibly hot out there is no fun, and it's not safe. You don't want a robot that isn't safe, and you want your developers to be able to move confidently in developing robots. And so we took what we think is sort of a third way that we're seeing more folks adopt nowadays, which is to use the Rust programming language. Basically takes a lot of the great performance capabilities of something like C++, a lot of the developer friendliness and semantics of Python with a great, even more type-safe wrapper, and gives you a language that can let your developers develop safely, move really quickly, and just execute incredibly quickly when compiled natively onto a machine like the Jetson. It's also actually got ROS capability created. This is ROS 1 I'm talking about here, but created by Adnan Adamovich, who's now a full-time engineer with us at Scythe. It's got support for the whole variety of all of the sort of basic ROS 1 types like client servers, pub sub, action servers, logging, all of that, and allows you to leverage all of the powers of ROS right next to the safety, performance, and ease of use of Rust, which has been really exciting for us. All right, and just sort of wrapping up here, by being really strategic with your software processing and your programming language selections, we think off-road robots can be just as capable as indoor or on-road AVs in the autonomy space that they're operating. You just have to be really intentional and think ahead to cover all of that. Now, I talked a lot about M.52 and what we're doing at Scythe, but I think there are amazing other opportunities for folks to build off-road applications, from agriculture to construction and mining to various types of off-road mobility. There's so many things and so many important applications that could use the help of autonomy that I'd encourage folks here to think how they can get involved and how they can bring more machines to these important areas of the economy and of the world that need help automating and getting more done with the people they already have, whether that's because they need to help people be safer in these environments. It's dull, it's dirty, it's dangerous. The 3Ds we all think of in robotics, so many different opportunities. They all have unique challenges for robots, but I think those challenges will really shape the solutions and the decisions that you make around things like hardware, perception systems, and computing to allow you to build better, more capable robots. We'd love to stay in touch with everybody here. I know I'll do a little Q&A here, but just wanted to throw these up. We're hiring. Join Scythe.com. Check out the open roles. You can follow us on social media. And then we've got our Confetti release, the open source Can Open package that's up on GitHub now. And we'd love to see requests, communicate with people there. And then our little blog that talks about some tech stuff and a whole lot about how landscapers can get ready for robots, because the change is coming. So thanks, everybody.
All right, Jack, that was fantastic. Thank you for sharing all that. It was great not just to see, this specific robot and what you've done with it, but also just to go through the product development process with you and see what it takes to, take something from idea to, I mean, what appears to be, almost, if not already, a fleshed out product. Are you working with specific landscaping companies right now that you've picked to help you flesh this out? Or is this something that's open to anybody who wants to use it right now?
Yeah, we're still early in our deployments, but we've got customers in Texas, Florida, and here in Colorado who are operating these machines day in, day out, turn lots of tall grass into short grass across all those areas. So we call it, this is our 5th generation machine pictured here. And we call it a pre-production unit. So we'll start scaling production sort of late this year and over the next few years.
Nice. One of the first big questions I have is, whenever someone comes to us or the Reddit community and says, I want to get into robotics, what should I start with? One of the best answers is a mobile robot, right? Because, the hobby ones are cheap. The open source stack for that, especially through ROS, is very quick and easy to implement. But obviously you guys have a lot of custom stuff going on. So what was kind of the first challenge that made you say, oh, this part of the open, ROS mobile robot stack or whatever's out there right now, this is not going to work with this application for these reasons? Kind of what was the first thing that made you think that?
We've built basically all of the software on our bots is custom from the ground up. Okay. We leverage ROS as a middleware stack as well, especially because the tooling like RViz is pretty unbeatable. But I think the computer vision, especially, my background's in computer vision, especially sort of geometric 3D scanning, SLAM, that sort of thing. And I've worked with a lot of open source packages, and some people in the academic communities have done really unbelievable work in pushing the boundaries of SLAM. But when it comes time to commercializing those applications, making them work every time with all of the hooks for your machine in there, I knew from early on that we were going to have to build that from the ground up ourselves.
Okay.
Thank you. I really, so my the master's group project that I did was a robot that was a tour guide for a campus. So we got to very briefly touch on the challenges of outdoors. And this is like seeing the answers to all my questions laid out in a 40-minute presentation of, segmentation was right, this, that, no. Really interesting that you were able to succeed where Tesla failed in saying we can ditch LiDAR sensors and still have robust autonomy. The video really does show that, it is navigating fine, and the segmentation to back that up was really challenging. So one thing I want, you talked a lot about the environmental impact early on. And then that to me struck me a little bit as an oxymoron in a sense that you are mowing the grass, and one of the best things you could do would be to not mow the grass. And there's a lot of hype now for rewilding and planting flowers. But that could definitely be a part of your business model in the future. So have you given any thought to how, where do we go when communities are moving beyond and homeowners associations are saying, actually, we want a field full of daisies instead of just neat, picturesque grass?
Yeah, absolutely. I think, things like xeriscaping here in the US that's caught on, in the West a lot, rewilding, planting native species. That doesn't mean there's no work that has to be done in caring for those spaces. They actually can require an incredible amount of work to keep looking nice, to sort of keep the undesirable plants out. And so, there's just going to be more and more opportunities for landscapers there. And then I think the other part is, sure, there are plenty of places where, very small home lawns don't need to exist in a space that's not used. Or in Las Vegas, perhaps they shouldn't have a whole lot of turf grass out in the middle of the desert. But people love grass, and just being able to have a space you can congregate on, like a field full of native wildflowers, very nice to look at, don't get me wrong, and I love that, but you can't play soccer on it. You can't have a picnic in a field of wildflowers. You still need these spaces where we as people can go and be outside and be together and enjoy a barbecue or a soccer game or whatever it is. And that is, I think, the large majority of the grass, the turf grass that's out there. The other thing is, I think through autonomous technologies and smarter technology, whether that's smarter irrigation controls, better mowing, we can really just, reduce the environmental impact of turf grass dramatically. I think it's something like half or 3/4 of the water used to irrigate turf grass is actually wasted because of either when it's done, it immediately evaporates on a hot summer day, how it's done, it's spraying a sidewalk instead of actually spraying the grass. And just by not doing that, we can already reduce that impact. So I'm very bullish on domesticated outdoor spaces. I think they'll continue to evolve over time, but I don't think that means they are maintenance free, if you will.
Really, really appreciate the answer there and the depth there. Very interesting. And I agree with you. These They are spaces that are essential to the way that communities function, and they're necessary. And as well, as you touched on the fact that, yeah, robots are well suited at optimizing efficient water usage for grass. And they can use sensors as well, as part of their being, whereas we have to use the sensor as a tool.
Yep.
Pass back to Mike. But thank you very much.
Yeah, thank you. I'll move over to asking some questions that have been posed in the YouTube chat now. Someone is interested in knowing if you're going to make a smaller model for personal use, if that's in the business plan in the future.
Yeah, I mean, our goal, like I said, at Scythe is to help humanity take better care of all of our outdoor spaces. And obviously a 52-inch mower is not the only tool humanity needs to take care of those spaces. And so up next, we'll probably go to a smaller mower after this, and then expand to all of the other tasks that landscapers do, like aeration and seeding and chemical applications and edging and trimming. I think the smaller mower, I think this goes back to the business model, though. We are a B2B company. We provide these machines to landscaping contractors to help take care of spaces. That makes it cost efficient to build such an advanced machine in a way that isn't for homeowners. And so even when we go to a smaller mower, I'm not going to make any promises that this will be something you can ever buy at Lowe's, because the price point for something you buy at Home Depot tends to be less than $1,000. And even then it needs to be perfect as a home robot. We all know how frustrating a Roomba that gets stuck when we think it shouldn't get stuck is. And think about that, but times 10 in the number of things that you have to do. And so we'll continue to provide these as tools for professionals to take better care of the world, and hopefully enable, by lowering the cost so dramatically, enable homeowners to take care or to take advantage of professionals in larger quantities than they do today.
Yeah, absolutely.
I really like the pay to mow approach, which obviously takes the weight off the customer. I don't know if you're aware, that's the same thing that is used in the airline industry. So when Rolls-Royce built their jet engines, they're only making money when it's in the air. And they've got very strict rules about how long it takes them to do repair jobs before they have to start paying fines to the airline company. Yeah,
that makes me feel much safer, because I don't really want Rolls-Royce making money when the engine breaks. I want them to be incentivized for that engine to last forever.
Yeah. Exactly. Yeah. Well,
a great question from the YouTube. Someone asked, if you had multiple of these robots out on the same field, do they talk to each other? Do they share mapping? Are they doing kind of their own independent thing, or would you never have them on the same field?
Yeah, today they don't share anything. Version 1, we'll call it. They're independent, so you can basically setting up an area. All you have to do is drive it around the boundary of the area. And so if you've got 3 machines mowing a 10-acre, soccer pitch, you could chunk it up into 3 separate 3-ish acre areas and just let them mow it. I think over time we'll move into that more collaborative mapping and execution mode. But as anybody who's done distributed robot work knows, that is still very much solidly in the land of R&D typically. So we're starting with 1 robot, 1 area, and we'll evolve, I think, especially as we go to those smaller machines, like somebody was asking about, to help them get more done collaboratively, even if they're only 30 inches wide instead of 52.
For sure, that's a challenge.
Someone asked, have you thought about carrying a small aerial drone on the mower for some like aerial pre-mapping or anything like that?
Yes, we've thought about it. Again, talk about coordination challenges between an aerial machine. And again, we want to make something that just works for landscapers day in, day out. The more moving pieces and sort of complex fiddly bits like drones and multiple sensor mapping, the harder it gets.
Yeah, lower complexity, less things to break. I mean, it kind of goes back to your, as minimal level of maintenance as possible, right? I had a question personally. I'm also a big Rust fan, but I know that, one of the big challenges still with Rust is in proprietary libraries. And I know that, trying to get Rust to talk well with like NVIDIA hardware, like CUDA kind of stuff, is still in its infancy. How do you guys tackle that kind of challenge?
Yeah, I didn't touch on that. I should have, but we actually, in full transparency, we use a little bit of Python and a little bit of C++, and a whole lot of CUDA language stuff on our bots as well. And one of the beauties of Rust is the FFI capabilities, the foreign function interface capabilities are really amazing. I don't know if anybody has ever tried to bind C++ to Python with Swig or Boost Python, but I mean, that makes you want to tear your hair out. And doing that with Rust is so unbelievably easy that we're able to, leverage open source packages like Series Solver, for instance, a great numerical optimization library written in C++ to its full effect on the robot, but put most of the compute up in Rust land, except for those areas we want to call down into, Tensor RT on the CUDA side or other GPU things. So we can sort of encapsulate all of the unsafeness or the non-rusty bits into very well-tested small pieces and call into it pretty easily.
Got it.
I noticed Confetti is also in C++, and I was going to ask, how do you mix and match those? So that kind of answered that.
Confetti's. I was just going to touch on this. So our firmware, our microcontrollers are not running Rust yet, and I think this goes to sort of the proprietary angle of compiling, proprietary tool chains and compiling down to microcontrollers is still difficult in Rust and not fully flushed out. And so our firmware is in C++, and Confetti runs both on our host Jetson system and in the embedded microcontrollers. And so we chose to write that in C++ and bind it into Rust where we use it.
Okay, yeah.
Yeah, nice.
With respect to Confetti, what you said you built up most of the software from scratch. Confetti was one of the examples of that. What did you need from CanOpen that you weren't getting from the why did you make Confetti as an example?
Yeah, so we chose CanOpen as the sort of higher level CAN protocol because it was what we saw a lot of our for instance, our battery modules, our off-the-shelf battery modules already talked CanOpen. Some of the other I think the ultrasonic sensors talk CanOpen. And so it seemed like the logical protocol to use on CAN. And then we looked at a couple of open source CanOpen offerings, but they were either deprecated or they had limited functionality. They didn't have the full object dictionary expressiveness that we wanted. And they were just kind of brittle and didn't seem like they had too much of a community around them, which is, always something you want out of an open source system. Make sure someone's keeping it up to date. And so, after trying that for, I think, our first couple revisions of the robot, we had sort of hacked up a couple of, one of the parts was we had a different CanOpen stack on the microcontrollers than on the host because these open source versions weren't quite cross-compatible on both platforms. And after doing that, we decided to unify them and bring them together to have our own system that worked really well. And that's been huge for us. Being able to customize the CAN behavior across all of the boards in our system means we can make something that's really safe. And I think that's the big part about owning your full stack is safety and making sure in all of those cases it behaves as you expect.
For sure. Is that a common process? You evaluate the current technology, and if you find yourself having to write a bunch of stuff for it, you just make your own. Is that kind of how you end up with a lot of custom software?
Yeah, I think so. I think there are some cases where because folks on the team have done that process in past lives, they just from day one wrote something custom because they'd already done the evaluation in the past. But, for instance, we're actually in the process of replacing ROS bags with our own internal thing. And ROS bags have gotten us this far and been a good data format. But I think there's just some critical limitations that we see to their expressiveness largely. And so we're making that transition now as well.
Yeah, nice. I mean, on even like a personal note, we've had people complaining in our community about the lack of CanOpen libraries. We've had people that are wanting to use it in their personal projects. So it's just really super cool that you guys made it open source, and maybe we'll see them using Confetti in the future. Yeah,
that'd be great.
Yeah. one final question. We have people in the chat asking if you would ever support cutting custom images or patterns into a field, for marketing purposes or something.
Yeah, I love that idea. Thing I learned somewhat recently, actually, if you know Fenway Park where the Boston Red Sox play, they've got the Red Sox in the grass out in the outfield. They actually do that with tiny streams of air where they push the grass down. It's basically like a 3D printer, but with air to bend the grass. And so a air blowing grass pattern attachment, I think, yeah, we'll see that sometime in the Scythe's future. Yeah. Oh yeah. Who
Awesome.
wouldn't want, their I don't know, whatever, their name in their office's front lawn.
I'm just imagining like every time high school graduation comes around, everyone has those big lawn ornaments with their kid's name on it, and just put it in the grass. Why not?
There you go. Exactly.
Cool. All right. Well, that's about our time we have for this keynote. Jack, thank you again for this wonderful presentation and for answering our questions. It's just been great to have you and to let our community, pick your brain about some autonomous mobile robot stuff.
My pleasure. Thank you for having me. And I look forward to seeing all the cool stuff everybody else in this community is showing off today. Really excited. And feel free to stay in touch with Scythe through our website. We got lots of different options. We'd love to talk to you soon. Bye, everybody.
Will do. And
we'll make sure
they are hiring.
Yeah, we sure are.
All right. Well, on that note, our next presentation, our presenters here, Kieran, with Ocean, they are building an autonomous ocean roaming sailboat. So Kieran, if you're ready, we are ready to hear your presentation.
All right, cool. Just a quick video audio check. Am I loud and clear?
Looks great. We can see you, we can hear you.
Awesome. All right, let's go. So my name's Kieran. I'm co-founder of a startup called Ocean. We're making autonomous micro vessels to collect ocean data. And today I'm kind of not going to talk about too much about the startup side of things. It's a great chance for me to talk about our journey and where we're at just now, and importantly show off some of our prototypes and just talk about the robot stuff. So looking forward to that. So let's start. Last year we were graduates at Imperial College London. We were doing our master's here.
Sorry to interrupt. Have you got a presentation you're sharing, or is it just camera?
Oh, that's not come up. Thank you for interrupting that.
That's why we've got to catch it early.
Brilliant. It's a permissions thing.
Okay. That's odd. Oh, on your end.
No, it's my computer screen sharing.
Got it. Yeah.
Okay. I'm going to need to quit and reopen. I'll see you in a minute.
Okay, sounds great. We'll catch you a second.
Hang tight, everyone. This is really good. They do some really cool autonomous sailboats.
Yeah, it'll be a quick fix and we'll see some great autonomous robot stuff. All right, we can see it now, Kieran.
All right. Cool, take two. All right, yeah, so I'm Kieran, co-founder of Ocean, and yeah, let's start with how we came about. So we're quite a new startup. We started last year from Imperial College London. Myself and my co-founder were studying our master's degrees. Anita, you can see on the right-hand side of the picture. She's been a long-time sailor all her life and did her master's thesis on path planning algorithms, basically optimizing a route for robots in the ocean. As part of that, we came across the Micro Transat Challenge, which has been a long-running competition. I think it's been going over 10 years now, for small autonomous sailboats to cross the Atlantic Ocean. And there's some rules to that. So the boats have to be powered by sail, no engines, motors, etc. They have to be less than 2 meters long. And in order to complete the fully autonomous category, they have to have no control signals after they cross that start line. There have been a success in the unmanned attempts where someone has remotely controlled the vessel across, but the fully autonomous category is still up for grabs. And loads of people have entered, DIY sort of enthusiasts, academic institutions, commercial institutions. And yeah, it's turns out to be really damn hard to make a robot cross the Atlantic. So we were inspired to give it a go. And so we started designing a boat. We made it all up in Fusion, 3D printed it in sections. We learned the joys of doing 12-hour prints and then having them fail right at the last moment and turn to spaghetti. And we found out about the painful process of hand wrapping fiberglass. And once we glued all these sections of the hull together, wrapped it in glass, really nasty chemicals and things to put on that. We had a nice solid hull and gave it a lick of paint. And did some design of the interior parts. As robots go, autonomous sailboats are super simple. There's only 2 real parts that have to move. You need to set your sail angle to the wind and you need to steer with your rudder. So we had some super simple sort of parallel linkage, worm geared mechanisms set up to control those 2 parts. We wrote some simple software just running off Arduino microcontrollers and gave it some tests on the local reservoir. And if this video is working okay, you'll see it sails super slowly, but kind of made it there. And you can see Wembley Arena in the background. So yeah, we were quite pleased. We demonstrated a proof of concept, but we were pretty sure that this was not going to be crossing oceans anytime soon. Part of the issue was the weight of the thing. So we left our 3D print inside this fiberglass outer, which made the sail incredibly heavy. Even with our 60-to-1 gear ratio on the motor there, it just really struggled to turn that sail through the full range of motion. And the 3D alignment parts we had inside very quickly sheared and snapped off. So things broke pretty soon. But we were inspired to, give it a better go, iterate on that prototype, and still go for this Atlantic challenge. And it was around the same time that we also came across ocean data, types of data like metocean, things like wind, wave spectra, temperatures, pressures, sort of weather effects, and then environmental data. You've got simple observations visually of the oceans, you've got chemical sensing of the water, passive acoustic monitoring, things like that. And we found out that one of the main tools to actually get this ocean data was to use sensor buoys. These are really simple passive devices, sensor payloads in a floating package. And right now you need to have a manned ship actually deploy these. They need to go out to an area of interest, drop them overboard, and then they'll last a few months in the area before they drift away with the ocean currents. So you get pretty poor coverage. These things will clump together. You'll have really sparse areas. And, if you want persistent measurement in area, these buoys will only last for a few months. And the worst part of it is they're not recovered. So they go on to just litter the ocean, wash up on beaches, because it's too expensive to actually go and pick these things up. And so we kind of realized there was an opportunity there to use these micro transat style vessels as ocean data collectors. And I will say that we are not the first or anywhere near up there in making robot boats. Robot boats have been around for a bit of a while. But what you've got on the market today tend to be much larger autonomous ships, and these huge expensive assets. They've got large power budgets, loads of expensive equipment on board. They're heavily regulated, have to be monitored by remote pilots. And they're just so expensive that you couldn't put them out in the same numbers as you do drifting buoys. And we want to design a system that is a lot more similar to your drifter than the research vessel. And I'll just skip back. I skipped a slide there. So the advantage of our system is that it could self-deploy. You could drop one of these things off on the coastline. It could, over many months, find its way just using the wind power to its destination it can use the wind to stay in that area, making measurements until near the end of its life, at which point it'll be able to sail back for maintenance and won't pollute the ocean. And the idea is that these are just so small, they're only about 1 meter in length, that they could be deployed by a single person, and you could deploy them in large numbers. Okay. So at this point, we decided to move away from just doing the microtransact challenge as a project to going for things as a startup with more of a commercial aim. And to start that off, we got some prize money from the enterprise lab at our university. We used this to sort of grow the team a little bit, and we started iterating on new prototypes. And importantly, we started going out to sea, which was really putting things through its paces compared to those reservoir tests. And we got things in up to a 4.6 on the Beaufort scale, which was pretty nasty to be in on a chase boat. One of the big things we did when we graduated as well is my co-founder and I put our sort of savings for the year together and bought a small sailboat secondhand to both live on and be our base of operations for all the tech development. So we had a pretty full-on few months of making our mini boats inside our boat that we also lived on, this tiny space with coffin beds. We'd be doing all the messy sanding, drilling, gluing, fiberglassing, where we ate and slept. It was a little bit hardcore, but all good fun, and meant that we could go out to sea on the regular, get lots of testing in, and iterate really quickly. And then it was a bit of a turn up in things towards the end of the year when we got some funding, and that's let us rent this workshop space. It means that we could move all of our development out of where we were living. It's a fantastic facility. We've got fully equipped tools, 3D printer. It's really nice to be there. We've had some media attention, which has helped, lots of people offering to help. We've grown the team a little bit. So things are going really well, and it's a fantastic life actually, spending time. We're based in North Wales, a little bit in the middle of nowhere, but we're very outdoorsy. We love sailing, climbing, and it's also ideal for testing our prototypes. So yeah, moving on to the tech side of things. So here's a video of one of the sea trials we've been on, with the vessel making some good progress and a bit of chop. You can see on the right hand side, that's one of our more recent prototypes, with some of the sensors on it. And what I'll do for the next part is I'll quickly go through the different aspects, and I'll sort of leave it up to you guys to ask questions if you want me to elaborate more on certain parts. So yeah, chatting a little bit about some of the main challenges of making a sailing robot. Because on the face of it, as robots go, it's one of the simpler things you can make. There's only a couple of moving parts, and the sea is particularly vast and empty space. You don't need advanced obstacle detection, slam, things like this. It's quite a simple environment as robots go to operate in. And the challenges actually come in with making something that can last for many, many months consistently, confidently. And part of that is in the power requirements. With the size of our vessel, we can realistically only have 40 to 60 watts of solar panel capacity on our deck, which really limits us to how much power we can use in our systems. That means that because the actuators controlling the sail, steering, they're the most power hungry parts, so we want to actuate as seldom as possible. So what we're trying to make is a system that is just controllable enough. It just barely gets where you want to go without using any more power than it absolutely has to. With the sort of scales you're talking about on the ocean, things could be a few miles out. That's pretty good going in terms of getting to a destination, monitoring an area. It also rules out certain platforms and things. So we don't really have the power budget to run even a Raspberry Pi that could run Linux. We can't use tools like ROS. We're limited to doing very low level stuff, microcontrollers. Everything runs on a couple of embedded microcontrollers. We write most of the C++ code ourselves, and that kind of comes into the robustness factor as well. Two parts to robustness. One of them is the physical robustness, The sea is a horrible, nasty place that will eat anything you put in it. Your electronics, your mechanical parts will corrode, they will break. But then there's also robustness in terms of the software. You can't have something that only performs in a lab setting for a quick demo. It has to perform consistently for months at a time, and you have to be confident that it's going to deal with interesting system configurations, bugs, things like that. So that's part of the reason as well that we try and write a lot of our own code so that we have full understanding of the code base, and we can be really certain of what's going to happen several months into a mission. Other things that make it quite hard are the sort of slow feedback, long development cycles. If you want to see how well one of these things is going to perform, you kind of have to take it out to the sea. We found that some of the models you can run on MATLAB, hardware in the loop, they're not very accurate compared to what you observe on the water. It's really hard to take into account the effects of large waves on small vessels. And you can't just test on your bench where you have nice diagnostic information coming in about exactly what's going on inside the microcontroller. When you're testing out at sea, you have quite a limited telemetry bandwidth to actually send over some system stats. So debugging can be quite tricky, and trying to work out exactly what went wrong when you're observing this vessel not going where it's supposed to. And then there's a bit of the system complexity as well. I think when I fire through, you'll see that some of these modules are quite simple. It's when you put them all together and everything has to work together, and that you find out how tricky everything can be. Here's some of the main components in the system. I'll quickly run through. I'll start off with a sail. You've probably noticed that it's not a conventional sail that you might see on a normal boat. It's a rigid wing sail. It's effectively an aerofoil, an airplane wing on its side. There was a lot of aerodynamic style analysis that went into this to try and optimize the shape. In our latest prototype, we've actually gone with a cambered wing, because it's got optimum downwind performance, but still optimizing for good upwind as well. For people that aren't sailors, essentially you can sail upwind, just not directly upwind. You can see the diagram on the left-hand side. You can go quite close to it. And basically you need to change your sail angle relative to the wind direction in order to get the most drive out of your sail. Quick flow through of what the insides look like. We've got some metal frames this time, and the electronics are kind of divided into 3 main modules, each of them enclosed in a waterproof shell. Then there's further waterproofing inside that. Again, the 2 simple actuator systems that do the mast and the rudder. The microcontroller we're using is one of the STM32 ultra low power range. This thing draws almost nothing. It's absolutely crazy. In standby mode, you're talking like nanoamps. It's got a whole bunch of hardware timers, so you can put the thing in sleep and it will wake itself up when you have certain interrupts or after certain times. Importantly, it has 5 serial ports, which really helps when we've got all of our different sensors that most of them use UART. It's got built-in timers. I love the watchdog feature. It's a fantastic thing to put in any projects you're doing. If the watchdog isn't petted, it will reset the whole system and turn it off and back on again. And everything's built around a real-time operating system. So you've got all the different concurrent processes going on between the control system, reading the sensors, etc. The 3 key sensors that you'd find in an autonomous sailboat is knowledge of the wind, strength, and direction. So you've got your anemometer, and we've got an ultrasonic one here, super expensive, but quite robust pieces of kit. You've got some way to measure your heading, so you can use an IMU for that. And we've actually been trying RTK GPS in a floating base mode. If you're not aware of what the RTK GPS is, it's basically a super accurate correction data applied to GPS. It means you're getting sub-centimeter precision in your GPS measurements from the rover relative to the base antenna. We've got our rover and base mounted at the front and back of the boat, and we're actually getting our heading information from that, which means we don't have to worry about magnetic interference, magnetic declination in certain parts of the globe. And it also gives us a really good way to measure when the heading information might be wrong, because it will report an incorrect distance between the 2 antennae. So that's super handy to know. And then the third part of things is your GPS, obviously, just your position in space. So those are the core navigation sensors. And then we've also got our data sensors. So important things are our temperature and pressure probes, which measure the surface temperature, subsea temperature, air pressure, humidity. Our grant funding most recently is for this project where we're doing passive acoustic monitoring. And we've put these hydrophone underwater microphones on our keel, and we're listening out for cetaceans, dolphins, porpoises, things like that, and logging that data. And we've also got our IMU on there using that accelerometer data to measure wave profiles. And these are super valuable to people who are running commercial shipping, offshore industry. They want to know exactly what the wave frequencies and wave heights are. A little bit about the stability and robustness considerations. So everything's like mega waterproofed. This is the chip that we actually plucked out of one of our vessels. This was inside one of the waterproof enclosures, inside the waterproof hull, and it never got even close to water, but the humid, salty air has managed to corrode all the terminals. So yeah, the sea is a pretty nasty place, and there's lots of considerations that go into sealing and waterproofing things. A little bit about the stability considerations as well. There was a lot that went into the physical design of the boat. The simple one is the roll stability. The lead keel on the bottom of it, make sure that it always stays upright, so that if it can it can capsize, but it'll always find its way back upright. What's a bit more complicated can be the yaw stability. So you've got to look at the aerodynamic and the hydrodynamic forces acting on the vessel, essentially trying to make it stay in a straight line as much as possible by itself. Okay, a little bit on the control system side of things. So this came out of my co-founder's master's thesis. She was looking at applying substandard algorithms like A* with a custom cost function to find the optimal path from A to B in the oceans. Obviously, such a small vessel is going to be infected by the wind and the currents. So you have to make sure that they're acting with you to get you where you want to go, avoiding particularly turbulent areas of the ocean. And this happens offline, generates a series of waypoints, which can then be fed into the next stage of the vessel control. On the face of it, quite simple. Again, you've got an outer loop which uses the GPS to say, here's my current position, where do I want to be, accounts for a number of different factors, spits out a heading to the inner control loop, and the inner control loop's job is to keep the boat roughly on that heading. It's got some additional logic to handle tacking. That's where you have to zigzag up against the wind, and lots of things to do with the actuator conservation as well. So it's making decisions. It's been told that it needs to get to this location, but it knows that if the sensors aren't working, or if it's used up too much energy already, it's going to ignore those commands and stay put for now. Next up's the power system. We're trying to run such an incredibly low power system. Our target is about 3 watts. The biggest consumers of energy are the motors in the mast and the rudder. So we're trying to actuate them as little as possible, which means trying to design a vessel that's just inherently as stable as it can be. We have capacity just now for about 40 watts of solar energy, which means that assuming about 2 hours peak per day, we can just about get in what we put out. We've also got a really large set of battery packs that mean that we could keep going for a week without any solar energy. A quick note on the telemetry. So there's 2 sides of this. One part of it is about getting the data back. We're using Iridium SBD for this. If anyone's used that before, you know, it's really small message sizes. You're talking about sending over a kilobyte. There's about 5 minutes latency on it as well. It's quite expensive to send messages. So it's really not ideal for debugging the system. We've built a dashboard that integrates with the SBD messages and will display the data and the position of the vessel. For the debugging side of things, we've got a LoRa link. So it's sending as much information as it can on the internal status of the system, any warning messages, things like that. The LoRa has a range at sea of just under 10 kilometers. So you can be on your chase boat. You might not even be able to see the vessel, but you can get information back about what's going on. And we've got a little relay station that we've built that just translates the LoRa information over a Bluetooth link, which means you can connect using your phone. All right, up ahead, we've got plans for our first Beyond Line of Sight mission this month, which is a bit scary, sending her over the horizon, but it's what she's built for, and looking forward to seeing how it goes. Next month, we have our passive acoustic demo. This is the end of our grant funding, and we're going to send it into an area well known for dolphin populations and see what we can pick up. We're quite optimistic because our vessel is sail powered. It should be super quiet compared to other solutions in powered vessels that are obviously going to interfere with the dolphin sounds. We've got plans. We've got a huge backlog of things we want to change. We're going to implement those starting in August and design our version 3 prototype. And that's all in anticipation of doing a data pilot with an industry partner in 2024. We're in talks with a number of different ferry companies, offshore construction providers who are interested in this ocean data that we can get hold of. And then we've got big plans for our Atlantic crossing too. We've definitely not given up on that. It's important to make sure that we have our commercial focus in mind, but yeah, we want to get in there and be the first to do the fully autonomous crossing of the Atlantic. Here's just a few things that we're looking to work on as well over the next few months. Some interesting ones are the sort of things we can do with Edge AI. A lot of the things we can't do, we have to do a lot of things online because we don't have the telemetry to send data back to be processed offline. And it's just really challenging, obviously, to do things like run neural networks on a 3-watt system. And there's some really cool chips coming out that claim that they're capable of running some really simple inference. So super excited to put some of that stuff on. We can hopefully do simple things like detect the marine mammal sounds and say whether it's background noise or a potential dolphin sighting. We've got some important work to do on wave profiles, so turning our accelerometer data into the best representation of the waves that we can get. That's one of the most valuable data types that we can produce. So there's all these problems that are kind of coming up, and I will say that we are looking to expand the team. We've been doing a few interviews just now. We are hiring. So if any of these things seem up your street, I'd be super interested to speak to you, and you can drop me a message. I'll put my LinkedIn and my email in the chat. And yeah, that'll do for the presentation side of things just now. Excited to answer some questions.
Yeah, thank you so much, Kieran. That was fascinating stuff. The whole design process seems super interesting with the decisions you've made with the like harder, airfoil sail and everything. Someone in chat is asking, they'd love to know more about the path planning system. Can you elaborate on it here, or do you have any resources online that kind of describe more about how it works?
So I will just caveat that I didn't make the path planning system. My co-founder is definitely the expert on that. Yeah. Can't give too many details on exactly how it works, and it's not open source because it kind of forms part of the IP. But in essence, what you used to use in order to navigate the oceans was pilot charts, which were a statistical representation of the winds and the currents in particular grid squares, taken from the last 100 years of data. And there's now some data-informed models that give you higher resolution on these winds and currents. So those were taken into account. There was a custom score, basically a function that took into account whether the winds and currents were helping you in the right direction. It took into account the velocity of the vessel. It also took into account areas that you just can't go in. Either the currents are far too strong that you'd be at their mercy, areas known for commercial shipping, and obviously the land. And yeah, perform an optimization to find effectively the lowest scoring route across, which should be the fastest, safest route.
Yeah. Okay, interesting. Yeah. And then another question is, are you using a lithium-ion battery or another version that's more tolerant to like sea travel or something like that?
So we started off using lithium-ion batteries. That's what was in the photo that I showed. The problem that we actually got with them was they have a huge range. So when fully charged versus discharged, or something like 2 volts difference, which if you start putting those in series, we had a system that could be at 25 volts fully charged, 12 volts discharged. Which is really hard to integrate off the shelf solar charge controllers. So most of your MPPT trackers are kind of designed to work with batteries in the sort of 12 to 14 volt range. So that became a bit of a nightmare. So we've switched over to LiFePO for batteries, which aren't the most energy dense, but they're pretty easy to work with. Their range is like 12 to 14. They just work with off the shelf kit.
Okay, yeah, great. And then, so you said that ROS was kind of too much overhead for what you guys were looking for in terms of like energy use. So is there no chance you'd ever integrate it, or do you think like there's some value in integrating it? Maybe if you increase your energy budget in the future, or?
I think a lot of the advantages you'd get from ROS are the sort of packages that interact with, computer vision and SLAM type things, which with such a simple system, I couldn't really see us needing so much. I would say that the better telemetry we can get, so if we can start to get things that are more like Starlink, where you can have huge bandwidth over satellite, and that opens up more doors for offline processing. But I think that would definitely be more valuable on the data side of things, streaming back the data and then, using big data analysis techniques on that. As opposed to using it, we wouldn't ever really look at running a controller offline and controlling remotely. I don't think that would work.
Yeah, that makes sense. Also just want to say, I mean, the whole buying your own sailboat and living off the grid on that for a while to develop this is just super mega. I mean, I know people go to pretty crazy lengths to, get their startups off the ground, but that's one of the craziest I've seen. Just living in a boat and doing all the layups and everything in your living room is just next level. So very cool stuff.
Yeah, it was a great time actually. It was hard. It was quite frustrating sometimes to wake up and find drill bits in your underpants and things, but you know what, I think I did love every minute of it. Just like this is such a change from being a student in London, and it just means you can go sailing all the time as well.
Yeah, absolutely. Well, cool. That's all the time we have for Ocean. Thank you so much for your presentation. This was really fascinating to learn about, and all the best for your company in the future. Hopefully some people in the audience are interested in working with you, and you'll get someone reaching out.
Brilliant. Thanks very much, Michael.
Yeah, have a good one. All right, next up, we have James Clayton with a giant walking spider suit covered in real flowers. So James, I see you're on here. Are you ready to go?
Yeah, I'm just going to pull up the screen here.
Okay, and we can hear you and see you, so you're good on those fronts.
Okay, cool. Okay, I've just got a little issue there. Okay, again, hang on. Okay, I may have to do the same thing as Kieran. They just quit and reopen. So I'll be back shortly.
All right, no worries. We'll see you in a second. Hope everyone's enjoying the third Reddit Robotics Showcase so far. This is fantastic, a really fantastic session so far.
Okay, let's try that again.
All right.
That should be good now.
There we go. Yep. We've got your screen.
Okay, great. All right. Sorry about the permission thing there. So I'm going to take us on a journey, and the journey is the journey of the flower spider. So I started on a few art projects back in 10 years ago, actually. And the projects were a couple of things. One, it was on the left there, you can see it's a washing machine that played the South African national anthem by flaring propane gas through homemade air horns. And that's kind of relevant because it just kind of shows the creative path, but also that I was starting to play and get experienced with kind of sequential or synchronized pneumatic control between music and MIDI tracks, and the control of you've got opening and closing of valves. And then the one in the middle there, that's a foghorn called Fogger, that basically releases fog and then warns people about it. So obviously a creative art project, same type of thing, learning more about pneumatic control. And then I also, around about the same time, started playing around with some, what you might call extreme vertical gardening. I'm very keen on putting flowers and vegetation on things, and managed to do that on something that moved around, that mini there. And then I got exposed to this piece of art on the right, which is Jeff Koons' puppy. I think it's in Bilbao. And thought, whoa, okay, you can actually cover an animal in flowers. And the idea came to me, which was to create an autonomous moving floral animal. So I really liked Jeff Koons' piece, but I thought it would be quite cool if it could move. And then I also thought that it would be very cool if it could actually walk rather than just move. And so the idea was, okay, cool, it's going to be a moving floral animal. It's going to go global. It's going to visit botanical gardens and parks globally, and it would be able to wear suits that have been grown for it locally and wherever it went. And that the idea of that is kind of to bring awareness to the kind of the edge of nature and engineering and the way we interact with the web of life. But also there's kind of a secondary thing, which is kind of to inspire and educate around maths, electronics, programming, and art. And I left robotics out of that stage because I wasn't really aware of robotics, as will become clear. So I then thought, okay, how am I going to make this happen? I came up with a concept and I found some 3D programming. I think it was SketchUp, and I drew it out. Said, okay, this is the thing that I'd like to do. Let's make it about 2.5 meters by 2.5 meters. Make it about a person's height, tall, 2 meters there, and then give it some floral suits like the ones that I've currently or had put onto that mini, and then give it some sunglasses just for the heck of it. So I then moved from concept to reality, and I got my first prototype out, which looked like this. And as you can see, this does not look much like that, but it was a step in the right direction, as you might say. And the broad idea there was to kind of just demonstrate that 2 legs could in fact work. It could propel something forward, and it was kind of within the limits of my funding budget. So that was good. I learned quite a lot about pneumatic control. I learned about sort of the physics of the whole thing, and incredibly difficult to make that thing walk just because of the weight of it. But it was all a learning process, which I think is kind of the theme of this presentation, is going to be one of learning. So then I got a bit more serious, and I started to build the spider up towards mechanically what it would look like today. And that was kind of drawing on my engineering background. So that went quite successfully. I got it to this stage. And mechanically, it was kind of running really well. And mechanically, it could move in the way that I wanted it to move. The pneumatics worked. I put some effectively pulse width modulation control through a couple of Mega 2560 chips on a sort of custom double Arduino, because one Arduino couldn't do what I wanted. And I ended up with this kind of complete spider, which was mechanically and kind of, I guess from a gait perspective, could do what I wanted it to do in terms of walking. It could be covered with these suits, which I was growing at the same time. And bingo, there is there's the effectively the finished product. And great. What I had planned was, okay, mechanically this thing's working, the suits are good. So, basically, I just need to pull out an Arduino, and it should take about a weekend. Got a whole weekend free. Kids go off somewhere else, got a few beers in, and by Monday, this thing should be walking out of my garage, based on previous experience. So it was a pretty tough weekend. Where I realized that I had in fact overlooked the entire field of robotics somehow, and that there was going to be a long journey ahead, and that the kind of the sequential synchronized approach to life was effectively an automaton which was not going to walk, and so that was quite sobering. So I didn't give up. I started learning ROS 1, Gazebo Classic, working through SDFs and URDFs, mainly through the construct, which was a learning resource I used at that stage, which was very helpful in getting me through the early stages of learning about robotics. And then I realized that I needed to have in place sensing. I learned, which I guess to the audience here might be quite humorous, but to me it was a revelation. I needed some orientation sensors on this thing, because I need to know where it is, and then I can say where I want it to go, and then I can effectively use some pulse width modulation to do that. So cool. So I banged on some orientation sensors, about 42 of them. And then at the same time, the realization came to me that no one else out there is doing pneumatic robots like this. And there's a very good reason for that. It's because effectively, if you effectively use an actuator, generally actuators, when you put them where you want them to go, they stay there. And you're not in a position where, in the case of a pneumatic cylinder, that it can move around, and sometimes quite substantially. So, knowing that, I then realized that each cylinder would have to have two pressure sensors on either side of it, in terms of determining what the force was, and then what the kind of delta force I'd have to apply to it to get it to move in the way that I wanted it to. So that was slightly irritating, or not irritating, but again, a learning journey. So I moved on to the practical sensor implementation piece. I put 42 sensors all over each individual link of the robot, and I then worked with a pressure sensor sort of manifold, a whole bunch of those, but another 42 odd, and that was particularly painful because of the voltage characteristics of the pneumatic sensors, and I guess another part of what I've experienced is that I have to work with what's practically available, and what was practically available happened to be these Honeywell ones at a reasonable price. I mean, they're certainly not top range ones because it cost a fortune, but there was going to be a voltage differential, which I thought was going to be fine, but a logic level converter issue cost me 6 months of my time just trying to work out what was going on, just because of I think it was a Texas Instrument pressure sensor that just couldn't push enough current through to the pressure sensors. So again, a kind of learning journey as you go. Very difficult to find online resources that can help me with what I want to do. But building up all of this great knowledge and kind of getting to a place where I can move forward in a good way. So where is it now? I've implemented serial interfaces to the entirety of the sensing system. I'm using mainly Arduino-based type microprocessors. Those are all onto ROS2 nodes, and they've got a ROS2 environment running onto an Intel NUC. You've got the whole pub/sub type setup there, mapping nodes, doing messages and topics implemented for the model and the live environments. I've got, I learned about Gazebo ignition again. Gazebo Classic was a tough call back then. It was easier this time around, but unfortunately the, what's it called when you've got the closed form? Yeah, closed form or closed loop kinematics, unfortunately, aren't on Gazebo Ignition at this stage, which was very sad because it was on Gazebo Classic, and this entire robot works off that time of closed form kinematics. And then, so yeah, again, another little road bump, and then loading it up onto RViz2 to effectively get a visual on what's actually going on there. And so that's the state it is at the moment. Effectively, this afternoon was putting in a noise filter on the orientation sensors because the orientation sensors in Ignition were creating unexpected noise. So which I thought it was going to be quite pure, but it wasn't. And then doing some, next up is SDF modifications to work with the weight distribution, because there's a lot of stuff on the Spider which is not equally spread across various links. And so I want to ensure that that's working properly before I start to do the gate testing. And then the big issue, which I guess I'm going to need some help with, I'm going to have a crack at it myself, is the pneumatic or the pneumo plugins here, where I've got cylinders on the Spider and the nature of the force that they apply, and how that is static or there's friction on them, and how it applies force, and also to what extent an incremental opening of a solenoid valve creates force on the Spider. That's all going to need to be worked out with an efficient pneumatic cylinder plugin. I haven't found anything online, and I'm also going to give it a crack myself first, so I kind of frame the problem. Then next up, looking at some additional hardware. So this thing weighs about 350 kilos, and so one is I need to put a bit of safety onto it. The first thing is, of course, the big red off button. The next up, LiDAR, to ensure that it really does need to be safe, because the intention is that at the end it's going to walk in public areas, and hopefully with some degree of red tape around it. But we need to have some more safety on it. And then just a control piece. I like the Sony Wii. I've used it a lot before, and I quite like the way of controlling giant robots with Sony Wii. I don't know if anyone else feels like that. And then the next step is to move from, post the Pneumo plugin solution, is to work with implementing FlexB. I only really recently discovered FlexB, and it super excited me that I could actually see a way of programmatically controlling individual services or actions or topic outputs to control the Spider in a way which could get it to some degree of gait. And when I talk about gait at the moment, I'm just wanting it can crawl. It can. It doesn't have to be doing anything. It's not a parkour type of project. Just walking or staggering or dragging itself across the road will be enough to start with. So the FlexB it's going to be a journey now with FlexB and learning that and moving forward, and then modeling it with suits, or so first of all without suits in the model environment, then with suits. I mean, the suits probably weigh about anything between 80 to 120 kilos, depending on how moist they are. And then moving on to testing the whole thing live. So this is what it looks like now, and moving forward, I'm heading in the right direction. I've got a lot of anxieties. It's not anxieties, issues, potential issues. First of all, there's going to be, my worries are around sensor noise in a solenoid-rich environment. There are 50 odd solenoids in there creating mechanical or magnetic noise. The mechanical failure potentially of the legs, especially in a testing situation, which effectively could bend a leg, and that's a problem because then I've got to get it fixed and get it rewelded, and that's potentially unnecessary, but I would expect that would happen. Third thing, water. The suits need to be watered, and so the suits need to be on the Spider because it's a heck of a thing to take them on and off. So water is a big issue. And there's a lot of potential points of failure. Everything that I've done there is in a waterproof box. Every exposed piece of kit that water could touch is in a ISO type environment or ISO boxes. So yes, it looks like it might work. Well, hang on, I can actually see something in that picture that isn't. But anyway, the more broadly, before I put the suits on and start watering them, everything will be waterproofed. And then the last thing is that the pulse width modulation use might destroy the solenoid valves. These aren't ones which were built for this. These are standard ones that I'm using. But the solenoid valves, which Metalwork, which is the company that I've used for the solenoids, their pulse width modulation kind of offering on the solenoid valve side was about 20 times more expensive than their standard ones. So I left it at that and thought I would just swap them out if they started failing. They make a lot of noise, and some of them make different noises from other ones given the same inputs. So that's also going to be something to iron out. The final thing I'm moving towards is, after I've got this thing moving, is to move out to engagement, collaboration, reaching out to community. I'd like to release the ROS package out for sharing and effectively for contribution of gate and control programming. Perhaps people can help me with that, or it can just be some kind of standing problem to solve. It might be that complicated, I'm not sure yet. And then the one thing is to community build and engage in the real world. It's like finding places where it can walk globally. So kind of talking to botanical gardens or parks or whatever globally and trying to work out some sort of schedule for that. And then the other thing is to let it wander in digital worlds as well, because given that it's I've got a model and it's SDF URDF model, I've got gate control. Effectively, that could be relatively easy, I think, ported into kind of Unreal Engine or Roblox and let digital versions of this wander into digital worlds, just because that feels like a cool thing, a way of letting it engage with the world. So that's kind of where I'm at. That's where I'm going. That's the journey of the flower spider. It was great to share it with you, and I'll be dead keen to hear any questions from you.
Yeah, so James, first of all, thanks for sharing this project. We really love seeing art projects on here, or at least projects with more of an art twist to them, because it's really special to see someone jump in, dive in head first, without necessarily knowing all the steps they need to take, and just kind of, resolve to figure it out along the way. So it leads to some super interesting problems like you discussed, not knowing exactly how to do certain things certain ways, and trying to engineer your way around them with the knowledge you have. It just leads to some super interesting projects. I especially like, I never would have thought about the problem of having to water the flowers, right? Like when I hear flowers on a robot, that's just not something I even considered. So it's super cool to see all the different engineering problems you have and how you're tackling them.
Yeah, thanks, Michael. It's as I said, it's been a journey, which involves resilience.
Yeah. Oh yeah, above anything else, I'm sure.
Before we lead into the questions again, thank you very much. I've been looking forward to this for some time. Again, for the unique take on a robotics project. You were mentioning at the end about simulations. ROS has Gazebo, its own in-house simulation engine, but then there's also others like Capella Sim and Weebots. And Weebots especially is very much aimed at a more kind of educational level. So rather than video game engines, you could look to the existing robotics engines. And if you're able to, make the model, the URDF available, then it's something that then people can play around with in their own time and potentially even, develop your robot from afar. But that's a bit of a stretch.
That's really cool. Yeah, thanks, Oliver. That's good input.
Yeah, it's really, really nice project. Lovely stuff.
Yeah, someone asked a question, have you checked its weight and soil pressure? I think that has to do with the pneumatics.
Weight and the soil. I'm not sure if that relates to its kind of penetrative, the load on an individual foot, as it were. So given that we've got one leg in the air moving at any one time, you then divide the 350 kilos by about 7, so you've got like 50 kilos, 50 kilo point load So I don't think that's going to go through soil unless it's wet, which yeah, I'm kind of planning everything at the moment, or going to be modeling it in an environment where a perfectly flat surface is assumed, and then start working with the reality post that.
Yeah, of course. From an engineering standpoint, the other input I would have is, have you, so you said that you have, sensors all over the robot that are communicating via, I squared C. Have you had any communication problems with those at all?
Well, not yet. Except that I kind of ran it across a 50-meter Ethernet cable to my study where it's warm because it's cold in the garage. But there were some problems with that which was solved. At the moment, no. Everything, the cables are working fine. Everything's quite close to the NUC, or at least to the point at which the NUC is communicating through Ethernet. But as I said, I am worried about the noisy environment. So I might be losing a lot of, I don't know, aluminium foil or something. I don't know. We'll find out what that will be when I get there.
Yeah. No, I asked because I have also in the past tried to use I2C over a longer distance, and it's really only meant to be used for maybe 1 or 2 feet, unfortunately, and I had problems with that. So I don't know if you end up having those noisy issues, you may want to switch to something like CAN bus or Ethernet that is more kind of robust over those longer distances. But yeah, no, I mean if you we love helping people who are learning about robotics. So if you care to join the Discord or the subreddit to ask any engineering questions, we'd certainly love to help and be a part of this amazing project you have going on.
Yeah, thanks very much.
Very happy to support it. Yeah, very much.
Yeah, I think part of the journey was being able to get to a place where I could articulate the problems that I'm having into a professional environment in a way that I could get response that was going to be useful. It wasn't just throwing out questions which were just no one understand what I meant.
Yeah, no, absolutely. That's kind of the first step of the problem, unfortunately, is kind of knowing what you don't know, right?
Yeah.
Yeah.
I'm still learning what I don't know. Yeah.
It's really fun seeing. It's really fun seeing that learning process in your presentation. A lot of us come from an engineering background, so we kind of have that intuitively. Seeing that process documented is really cool.
Yeah, absolutely agree. We have a quick question from the YouTube live stream. Have you thought about putting pressure sensors or something on the feet so that could, maybe someday handle walking on, not completely flat surfaces, being able to kind of sense where it's walking?
Yeah, that's kind of, I was going to say next step, but the approach at the moment is to position the foot where the flat surface is expected to be, and then apply force such that based on the cylinders, the cylinder pressures, that leg is applying 50 kilos of force to the ground. And so that's putting a pressure pad at that point would be the next thing that I would do. Yeah.
Great. Yeah. Any of the moderators have any final questions?
No, it's just all very interesting. There's more that I want to think out and reflect on than ask questions. But again, it's a fantastic project, and you've done so well to get it to this stage. And would very much like to see it continue development in the future. Yeah,
that's the plan. And I've actually got to given what I've learned, I've actually now got my first timeline. I actually think it will be working in January of next year. So I think I know enough to be able to actually put something down that's scheduled, rather than just thumb sucking.
Nice.
That's great. Yeah.
That's by the Discord. I'm sure we'll be happy to help out if we can.
Yeah. If you get it working, we'd love to see any videos. Yeah.
Yeah, cool. I'll let you guys know. It'll probably go straight through that door and over that trailer.
Yeah. Cool. Well, all right. In that case, let's go ahead and move on to our next presenter. Jacob, are you ready to present? All right. Well, in that case, James, thank you so much for your time. Well, please stop sharing your screen, and we'll let Jacob start, and we'll hear from him.
Okay, I'm just gonna drop out of the. Try and work out how to get out of Zoom here. Hang on. Oh, there we go.
Yeah.
Okay.
Thanks. And Jacob's going to be talking about SLAM via blob tracking and inertial tracking. So whenever you're ready, Jacob, please take it away. Yes, you can start.
Can you hear me?
Yeah, yes, we can actually hear you. Yeah.
Okay. I'll just go. You guys can see that?
Yes, we can.
Okay. Yeah, so I'm presenting this robot. I don't know if my camera feed is still there, but I have it in front of me too. But yeah, I'm a hobbyist, you know, so I don't really have a heavy robotics background. I spend most of my time like developing web apps. So, but yeah, you know, like Raspberry Pi, Arduino, I like to work on that stuff. And this one's trying to do room navigation. So let's see, 10. Okay. I started out with version where it was like camera, and then it had a LiDAR, an ultrasonic sensor that would point. And this one was like a bad design because of the stiff wires. So it was like hard to aim it and have it recenter. Originally, it was designed for these like round steppers, but you know, you just go in like a direction. You don't have like positioning without like some kind of encoder or something. So yeah, I built this thing and started to get all the parts working, talking to each other, how to pull information. And then I also was like starting to map things in 3D, like using 3JS. So I'd plot the, you know, points in space and have an idea of where things are. And then I wanted to make that like smaller and more compact. So I designed this thing that sticks like a pi zero. There's an IMU at the center of all the axes. And then the two depth sensors are there, and then the cameras in the middle. Then the entire thing like pan tilts. So it was, I had to like design that and then solder everything together and then get it working. I was having problems with the I2C working, the separate channels, so I put everything on the same one and ended up swapping out the 6050 for 9250, the 9-axis one, which was bad because it's bigger, so I had to like get it in there by breaking stuff. So it's like a little wobbly. And then the camera, I didn't realize I'd have to flip it upside down because of the ribbon cable or flat connector or whatever. So yeah. And then it's a separate unit. So this robot here is like electrically separated, different system. It uses a WebSocket to control it. So this is just like a brain that, you know, scans and then tells it like where to go. And then yeah, so this is the actual like navigation process. It produces like a panorama because this camera lens takes small pictures. So it takes 15 of them and then stitches them together, which I initially tried to like stitch them myself, but it's not an easy process, it turns out. But thankfully it's built into OpenCV, so that's what I'm using. And then I'm using the color masking to pick colors out and make the blobs. So I'm using 1D, 2D histograms to find those. This is a really, really bad way to navigate, and it's like a slow process, but I don't know, it was a way I came up with. And then, you know, once you know where the things are, you can point your beams at them and measure how far away they are, and then as the robot moves, you like track them. So that's the process. And then here you can see, sorry, the messy room, but that's what kind of environment it operates in. This crosshair thing here is a way to figure out where the camera is. This is like the center of the camera. And when you like do the panorama, it merges pictures. So this thing, which used to be like a perfect X, but there's always a way to find the cross by like sampling. Oh my bad. Sampling the slope and finding an intercept. It's really cool. Like if you had a panorama, like, and you knew where the center was, but this is the way I found to make it work. And then, yeah, so there, you know, like where your camera is with respect to the panorama. And then this is like an example of a orange mask applied, and that's like a target. And then this is more info on the whole like HSV range thing. And I think this is like some form of color segmentation, it turns out, but I didn't know that at the time. Just like based on like that concept, like find the red ball. So yeah, and then this just showing like these sensors, their beam sizes. So I don't know, 25 degrees is pretty big, like, but the TF Mini, it's only like 2 degrees, but it seems to be more useful when you're like measuring far away. So you kind of combine the two to like check things. See, you got 5 minutes, okay. And then just IMUs, like so far I've only done like dead reckoning and estimation of displacement and then rotation. That's what's determining like the angles of the servos and where it's looking. Of course, that, you know, is not as like guaranteed as like mechanical encoders or something, but that's what I wanted, is like a thing where it just relied on the IMU for the positioning. And then this is just information on 3JS. Like this is another robot I made where it uses that same idea, like a single beam, and then it's like wiggling the entire body to, you know, make a depth map like this, which is like terrible because you're moving 12 servos versus like 2. And ideally you'd use one of those lidars where it generates like a giant, you know, point cloud or whatever. But yeah, so, and then you can import like 3D models in 3JS, so you can build like a simulator, move individual parts and all that. So that's pretty cool. And then, yeah, this project has like problems, you know, like you don't know how big something is in a picture. It's like perspective. So, and then the body, like the way it's designed, like when it moves, it shakes, and then the IMU like picks that up, so you have to take that out. Yeah, and then if you want to see more of it, there's the links.
Awesome. Thanks for your presentation, Jacob.
He still may not be able to hear us. Let me message him real fast.
I hear you now. It's
okay, great, wonderful. Okay, cool. That makes this a lot easier. So really amazing presentation. I love how cleanly packaged everything is in that little tiny sensor bundle. I think, you know, a lot of people would be interested in taking that sensor bundle and putting it on their own robots, you know, if they're working on their own. And then, I mean, the web interface is fantastic as well. I mean, a lot of people in the robotics community know the pain of compatibility issues, you know, running a lot of stuff in Linux and having stuff not run on Windows or Mac or some other OS. It's nice to be able to have everything run in, you know, just a web app so that there's no real compatibility issues. So that's super cool.
Yeah, and JavaScript is I would say a great language. For me, it's like what I primarily use, and you know, you can just throw anything in there, you know, arrays of random types. So it's great.
Yeah, of course.
Did you have a package that you used to use all the different sensor values and the camera and everything, or did you do that yourself?
I would look up like libraries, how to like talk to the TF Mini in I2C, and then I would write a class wrapper around it and then merge them together. I don't say I wrote the code from scratch, but you know, yeah, wrote all the like individual pieces after I looked up how do you like read a value from this thing and then put them together. Same with like the OpenCV stuff. I pulled a lot of it from like Stack Overflow, and then after that, I start building the system together. Like I don't know if you can see the camera, but the body is using a Arduino, like that's C++ like Arduino, and that's a different. I wrote that too, but it's using like the servo library. So
Yeah.
Are you using the Arduino?
yeah, on the body I am.
Yeah, that's
right there.
Yeah, that's a good
yeah.
one.
We use the seed controllers at my work. They're really tight little packages. So.
Mhm.
Yeah, and then there's a ESP01 on there. Those are great.
Yeah. Have you run into any issues with like the computational power of the like a Raspberry Pi Zero on there? You know, have you had any situations where you wanted to upgrade to a more powerful, you know, SoC?
Yeah, this one is a 2, so it's quad core. I bought this like when it first came out, 2021. So I was lucky. You know, it wasn't like $80 or whatever. They marked them up now.
Yeah.
But yeah, I do feel it like on the single core when I'm running something and it takes like 30 seconds versus 1 if you run on a desktop. But yeah, a lot of it, well, it does take a while. Like the panorama generation, I think takes like a minute to stitch the 15 photos together. So yeah, it's not great. It's definitely not like a monocular, you know, VIO 30 frames per second, you know, nothing like that. It's very crude, but it was like tangible for me.
Yeah, I mean that's plenty. If you get a robot moving around and doing things, that's way more important than being a little bit faster. Yeah, very cool project.
Yeah. Thank you so much for sharing. This is really fantastic.
Thanks for the opportunity. I was surprised I was picked. Like, no way.
No, of course. We love having all matter projects on here. So the more diversity, the better in terms of, you know, what your project does and what your ability level and what you're going for is, right? So we're just happy to have everybody. Well, cool. We're running a little bit ahead on time, but if our next presenter, who I think is already in the chat,
Yep.
Yeah. So I mean, Dimitar, if you're ready to present, we would love to have you. Thank you again, Jacob.
Yep, thank you.
Hey guys, can you see me?
We can hear you, but your camera feed appears to be. Oh, we can see you now.
Oh, okay, it's good now. Yeah,
Yes,
is
we
the
got you now.
microphone doing fine?
Yeah, we can hear you great.
Yeah, okay, great guys. Great presentation so far from all of the previous participants, and I would like to thank you guys, the organizers, for hosting this event. So let me just share my screen.
Our pleasure.
Just a sec. Okay, so probably you can see my screen right now, I think.
We can see your screen. Yep.
Yeah, okay, so let me start off with the presentation. Just need to hide this from... No. Oh, okay, I can just pull down the Zoom thing. Okay, so... Well, welcome. Hello, everyone. I'm Dimitar Bejanovsky. Welcome to my presentation. I'll be presenting today my creation, the mobile UGV platform. So, hello, first of all, and let me introduce myself. Who am I? I'm a software engineering student here from North Macedonia. I'm studying basically computer science, and I'm working as a software developer, and also have a passion for electronics, which I later transferred it into robotics as a hobby. So it's like a side thing that I'm doing. So how did this all started? It was back in COVID in 2020 when we all got locked up, and something weird happened. I suddenly had a urge to buy a 3D printer, and it turned out to be one of the best choices I've ever made. It turned out to be a very nice hobby. This is the previous robot I made. I will later showcase the current one I made. So it's basically a 3D printer robot. It's not very, let's say, well polished. Let's say it was like a first attempt at combining all of my skills with electronics and stuff. And I just wanted to add more and more features to it. I did not have any like certain tasks that I wanted to accomplish. I just wanted to add more features and try out things. So I found like a huge laser that I kind of overvolted, and it turned out to look like a lightsaber at the end. So that was very, interesting to do. Here's another showcase of the robot, and this robot has a Raspberry Pi on it. I used the Viola Jones algorithm with OpenCV to use face detection. I'll play the video intro here. This is for the previous robot, basically. And so as soon as it detects your face, it puts a square in it. And depending on the size of your face, if it's like close to the camera or forward, there are two thresholds that need to be in check if the robot should move forward or backward. And these two red lines are like borders. If your face goes in one of these lines, your robot will go like either to the left or to the right side. So this way, like even with like a CPU device like the Raspberry Pi, you can have like an autonomous, robot following you around. Basically, that was my goal for this thing to be somehow the robot to be autonomous without like any machine learning skills, because I did not have any ML skills back then. And that is the showcase for this robot. And let's go to another slide. Okay, so that robot was called Ricardo. It was a great first attempt. Here's a picture of it trying to drive around in snow, but it needed upgrades. It was not modular. I mean, it kind of was, but you had to strap things on it and like tie it with something. So it wasn't very, very smart, a very smart thing to do. And it also needed features such as LiDAR to do some sort of like autonomous navigation, or like at least have the ability to perceive the environment. It was also lacking robustness. Like you did not have the space to put on speakers like the current robot, which I'll show you in a bit. So I needed something better. And this is the name of the new robot, Gravis. And this presentation is like a mobile EGV platform. That's like the category, but this is the name of the robot. So when I started making this robot, I wanted to refine a bunch of my skills like CAD modeling, machine learning, and project planning in general. This project turned out to be like one hell of a thing to manage, because there's so much like sensors and stuff, and it's truly a problem when you have a bunch of features. So okay, let's say you have a bunch of features that you want to accomplish, like the requirements of the robot, like a LiDAR which you can perceive the environment, a robot arm which can pick up things, light things up, way to light up your surroundings, speakers so you can play something, or like make the robot smart in the future, and so it can communicate with you if you integrate a microphone afterwards. And all of these things, and like all of these things, you have to imagine or like put in your head what the robot has to look like up front, and then you have to like pick up which parts you're gonna need so that you can like make the 3D model of it, which you can later 3D print. So it's like you have to be like always thinking 100 steps in like the future. So because if you miss one thing, like if one dimension is not according to plan with the electronics, you're just gonna mess up the entire project in the end. So it was like a huge overhead to think always in the future with this project. And so I wanted to learn these or improve these skill sets like CAD design. I used SolidWorks for this, but I did not know a lot, so I had to learn it to develop this model. So here is the robot here. Here is the full 3D model of it. So it was like a very intensive process for learning this and putting everything together all in one place, so that you can have a virtual thing which you can later put in like the 3D printer. It can come out to the physical world, which was very rewarding to see. But what is Gravis? It's basically a modular robot, which can be adapted according to specific needs. Let's say because it has a camera and a lidar, you can use it for home security, for it to roam around your house and monitor it. Basically, it's mostly 3D printable, except like these lower chassis, which are like aluminum. And it has a lidar sensor, speakers which are very reliable, which we'll test out in a bit. Lights so that you can the robot can be noticed and these can be animated, and also the camera has a pan tilt which you can rotate and everything. Also, you can upgrade this robot depending on your needs and all. When I designed this robot, I'll put on the SolidWorks here again. As you can see, there are a lot of holes over here. So each hole is like 3 millimeters in width, and each hole is 10 millimeters spaced apart. So all of these parts you see here, let me turn on this. All of these parts you see here, let's say the Raspberry Pi, it's in its own holder. So you could just, if you need the Raspberry Pi in a different place in this robot, you can just move it around basically. That's the main idea of this thing, to be fully adaptable, and you can swap out parts on the fly, let's say, because everything is just being held on by a screw. There's no like there's nothing like that's glued in that you cannot change. That was the main goal of this robot. Here's a picture of it without the case. I later designed the case and 3D printed it. And so these are the lights of the robot. There are, I think, 10 watt each. I mean, there's a front and back LED strip which are programmable, and I think there are 10 watt each, 10 watts each. So this is a picture of my backyard, which is like pretty dark. And here's this with the front lights on, which like it lights up the entire place basically. So let's go in a bit more technical deep dive in terms of the electronics here. Okay, first of all, components. So this is like an exploded view of the robot. It has our RP LiDAR A1, which is, I think, the most common 2D LiDAR. It has two speakers, which are, stereo speakers. I custom made the speakers, basically 3D modeled them, and I got the audio amp off of AliExpress for $3, and it's super loud for $3. It has a 3S LiPo battery, a camera, and a robot arm. The main computer is a Raspberry Pi, and it feeds data to the Arduino or ESP32. Currently, I'm running the ESP32 on it to read serial data from the Raspberry Pi and control the motor controllers, LED strips, camera servos, robot arm, and everything else. So I wanted to make like an interface so that everything can be like abstracted off into a separate microcontroller. So this is the electrical schema. Here we have the Raspberry Pi connected to the LiDAR. Currently, I don't have the microphone set up. This is the final phase of the robot, but I am still developing it. The Raspberry Pi is connected to the ESP32. We have a bunch of sensors here, like the IMU and the gas sensor and DHT22 for temperature and humidity. Each are connected to the sensor connected to the ESP32. Also the motor controllers and the servo motors and the LED strips. And basically it's the ESP32 is controlling everything, and the Raspberry Pi is just like, telling it what to do. I have two switches here. One is like a safety switch for the motors so that it doesn't, right off the table during if you're developing code for it, and the other one is just for for everything else. I have a 3S LiPo battery, which is 12.6 volts, and I'm using off-the-shelf AliExpress step-down DC voltage converter, which converts 12.6 to 5 volts so that everything else can use it basically. If anyone needs the schematic, let me know. I'll give them access to it. So here's a video demo of the robot, which I'll play right now. Okay, let me just unmute this. So currently, its autonomous features are kind of limited because it's mainly like manual control. But with the LiDAR, I'm developing the autonomous mode for it, and I plan to integrate ROS for it. But currently, it has all the hardware capabilities for, let's say, autonomous navigation. And here I'm just like, if you can see here, I'm reading the LiDAR data to map out the room, and I have live camera feed for when you control a robot. And so these are the speakers of the robot. Which are pretty, these are also the LED strips, which can be controlled basically from a web interface, which can change colors and everything. And this is a robot driving around. Okay, and now I'll just control it. Control over and drive around my apartment. As you can see, it's over here in the field. And right now the camera is a bit tilted down. Yeah, Murphy's Law. So okay, the camera is kind of not tilted correctly, but depending on the controls you use, the robot will drive around basically. You can drive around in manual mode, and you cannot see much from the camera because it's kind of disconnected right now. It's not tilted properly. Yeah, we'll just ignore Murphy's Law for now. Yeah, you can see this, but it's not like held in place because it got loose in the end. And here is the visualization for the LiDAR data, which is being generated with OpenCV. And it's like mapping out my room in real time, as you can see right now. Let me just point it like this. You can see the robot, light mode on, and you can just drive around like this. Okay, so I want to demonstrate to you how low the speakers are. I'll just play it here. So I'm playing this from the robot. So this is like live.
I think your speakers might be not being picked up by the mic.
Oh, yeah, probably it's being filtered.
We'll take your word for it.
Yeah, I'll send a link for the video for the demo. And
yeah, that'd be great.
Yeah, you guys can see the demo for it basically. So let me get back to the presentation. How do I exit? Okay. Okay, so yeah, future plans for this robot. I want to integrate ROS in it because currently it's running on Python loop. And basically it has 3 threads. One is for the OpenCV data for the image processing. The second one is for the keyboard listening and its input. And the third thread is for the real-time rendering of LiDAR data. And for the future, I plan to integrate a Jetson Nano into it so I can run some ML models on it. And I'll add like a full autonomous mode with its next iteration of it. And also learn lessons. Hardware project management is pretty hard because there are a lot of things that need to be connected in between and everything has to go smoothly. And since in Macedonia, we do not really have any like stocked out hardware stores, you have to order it from online and there's like a 1 month delay. So like one thing, if you forget one thing, it can like set you off 1 month in the entire project thing. And you always have to think like 100 steps ahead. And because of this, good requirements in the end will result in, good results for the project and everything else. And if anyone has any questions, I'll be happy to answer them. And this is also my LinkedIn, where you can contact me for either about the project or any collaboration or any, if you just want to chat of it, basically. So thank you for your time. I'll be happy to answer.
Yeah, thank you so much for presenting. That was really, really great. Good to see like the whole process start to finish of like what it really takes to do all this integration and build a mobile robot that has all this functionality. So I mean, in terms of like real world use cases, have you thought about where you want to see this being used? Is it like an educational platform, or would you like to see it being used in some kind of real world environment to accomplish some task?
In terms of educational environment, there is potential for it, but I think it's there's a lot of use for this robot, like when for inspecting places which are like hard to access. Like let's say if you want to inspect the underground, like under a car or something, or somewhere there's like a confined space. So I believe it's more like towards the inspection part of it, or even in like places which are pretty remote. If you just attach like, let's say, a solar panel to this robot and add like cellular connectivity, you can just have a remote agent that is monitoring your facility or place or something, so you don't have to have a real person on site for it, basically. So it's like, in terms of use cases, I see it more in those areas. And also education is a potential, but I'm seeing it more in the industry ways.
Okay, great. Yeah. What kind of battery life does it have right now? Like how long can you run it around off charger?
So it has like 5,000 milliamp hours, and when it's going idle, just playing audio and you driving it around occasionally remotely. To be honest, it's doing pretty great. If it doesn't have a lot of motor usage, I think it's like gonna go for 6 hours or more. And like with intense motor usage, I think 3 hours it's pretty good. So
okay,
it's going pretty good on that part.
That's not bad at all. Okay,
Very
well,
cool presentation.
Yeah, really fantastic presentation. That's all the time we have for this presentation. But as always, our presenters are around if you want to ask them more questions about their stuff. You can find many of them in Discord and on the subreddit, or sharing their own ways to get involved. So thank you again, Dimitar. That was a really wonderful presentation. And next up, our next presenter is going to be Saksham Sharma with a multi-robot path planning algorithm using a priority-based method. So Saksham, if you're ready to present, we are ready to hear your presentation.
Hi.
All right, we can hear you. Go ahead.
Okay. So yeah, just a correction. So it will be me, Saksham Sharma, and Naman who will be presenting today. So Naman will be starting off.
Yeah, can you hear me?
Yep, we can hear you both.
Okay, that's great. So, so this is our Reddit robotics showcase. We are presenting a multi-robot path planning algorithm. It's a lot of words, but we'll break it down. It's not something very mechanically oriented, but it's more towards the algorithm side. Let's just show a preview of what we are working on.
Naman, we can't hear the audio.
You can't hear?
No.
Okay, so a small overview of how our presentation will go. We'll have like 8 steps, describe who we are, introduce what the problem is, and go through the algorithm. And we'll have a little bit of comparison with one of the algorithms that are already there. And towards the end, we'll show what we did in real life, and you can obviously ask us questions in the end. So who are we? Both of us are students from Bangalore. We studied electronics, and we are working in robotics. I mean, I'm working in robotics, and Saksham is going to be working in robotics soon. So, Saksham.
Yeah. I mean, like, funnily, we have a pun where we say that we are those overworked, undervalued humans, which are striving and working towards making those bots harder, faster, and stronger from what the contemporary ones are. So, with that notion, we'll begin the presentation. Can you move to the next slide?
Yeah. So an introduction to the problem that we have at hand. So if you look at factories nowadays, there's a lot of robots moving around, a lot of autonomous mobile robots moving around. And what you notice is one of the biggest cause of problems is anytime these robots collide. And the way these systems are usually set up is that once it finds an obstacle in its way, it'll just stop, it'll raise an alarm, and it'll wait for a human operator to come and fix it. And what we want to do is to eliminate that problem by making it autonomous to run these robots and to avoid collisions and to adapt to newer environment changes. And this task typically has two approaches, a coupled and a decoupled approach, where you consider the plans of all the other robots or you don't. And there are some existing decoupled approaches called SIPP and CBS. SIPP was presented by CMU. CBS it's a complete and an optimal solution that is claimed, and it is really good, but what happens is it might take too much time, and what our algorithm does is try to circumvent that and take a shorter amount of time to find a path which is better than finding an optimal path after a long time. So this is the problem statement that we formulate. The entire environment is discretized. So each point is a set of XY coordinates, and the map defines a static obstacle known in the environment. This is generated through SLAM or some kind of occupancy grid, which will be in the map fed to the robot prior to its operation. There are RI robots with I unique start points. So 4 agents, 5 agents, 12 agents will have R12. And planning and execution is done in a frame by frame system. So we synchronize at every second. And so from XT to XT plus 1, we know where the robot is. And what we do is we ensure that the robot isn't colliding during that T time. And so one drawback of our algorithm is we need to synchronize at every frame. So we need to know where all the robots are at the end of one time frame. Collisions is what we define. There are two ways. One is a head-on collision. If two robots are just straight ahead with each other and they hit each other, that's a head-on collision. And an interchange collision is where two robots are at two different points and they try to cross over. So one is at X1, Y1, and it's moving to X2, Y2. And the other one is at X2, Y2, trying to move to X1, Y1. So since our world is a frame-based world, we can't really assume things that happen between XT and XT plus 1. There's no XT 0.5. So to ensure that, we call this an interchange collision, and we just try to reduce these two collisions in the spatial domain. So the algorithm is going to be explained by Saksham.
Okay, so but jokes aside again, usually, so till now, people have tried with decoupled approaches, but they have more or less tried in the space of using A-star couple search. So one of the key improvements which we were able to do was using D-star, and D-star is able to use memory to keep certain locations value when it's like solving a path planning problem, it'll save those values and then reuse them again when it is trying to find a new path because some obstacle has changed. So the way we try to use that is we talked about, Naman talked about having head-on collision and interchange collision, right? So let's say a certain head-on collision happens between robot 1 and robot 2. Now we want to avoid this. So we have set up let's say a random priority order. So robot 1 has to be given space and robot 2 has to wait for it. So what we will try to do is we'll try to introduce a virtual obstacle in the path of robot 2. Once we do that, we use the decouples efficient recalculation method so that now the robot 2 doesn't have to recalculate its whole path again. Robot 1's path remains the same, but robot 2 will just change its path, saying, okay, this is a new obstacle here. And that obstacle will remain on that particular for that time frame. So we're also considering the time and the frame of like where we reach, which frame we reach at that particular time. So both the things, location and time, are being considered by the approach. So I mean, yeah, so now you think of like, okay, there are 100 robots path their own individual path. Once they plan their individual path, then they will see, okay, depending on what our priority order was, certain will try to relocate, and we will see that in coming up slides, how they are able to do that. And so, yeah, so when they will try to do that, and then they'll try to find an efficient path. So this is how we are able to sort of achieve that decoupled nature and keep the complexity low. And compared to what CBS and SIPP have done, we are able to reduce our time. Moving forward, we'll look into more how like ROS is being implemented for the project. So that Naman will explain.
Yeah, so we are using a kind of client and server structure. So if you've used MoveBase, those kind of action servers are what we're using, but it's a little counterintuitive in the way we have set it up. So conventionally, you expect there to be a server and all the clients connect to it, but we are doing it the inverted way. So each robot is considered a server, and the action that we tell is go to an XY point, and all of them go to that XY point. And once we listen to all the go-to results, since as a frame-based system, we need to ensure that everything is synchronized to that frame. So as soon as all of them return a go-to result, we move to the next point. And we can do that for n number of servers, and we just need one client row. Client is the centralized control.
So yeah, as I promised, we'll do a quick rundown of how that algorithm worked, right? We'll see how those relocations of the decoupled path happens. Can you move to the next slide, Naman? Yeah, so consider this is like the initial start point, right? All the 6 robots have plotted their way individually on their own. They're all decoupled. They don't know what the other robot is doing. And obviously, so the XZ axis you can think of as the timestamp. So you can see a lot of robots colliding with each other. Now, like moving on. So the next step of the algorithm is first it'll try to detect it. So it saw that, okay, between the robot 0 and robot 5, there's an interchange collision which is happening. It'll try to avoid that. So the way it did it was there was a certain priority order. Robot 5's priority order was lower than what the priority order for the robot 0 was. So you can see only robot 5 is changing its position, not the robot 0. And this is, I mean, the way we are trying to find the shortest path, or the collective shortest path, right? Another thing which we didn't in detail discuss earlier was that how do we come up with this priority path? So can you move to the next slide? Sometimes what will end up happening is, this is like the final state. So algorithm says, okay, this is the final position. There's no collision else happening. But think of another way where priority would have changed between the robot 0 and robot 5, or there's some other collision which tries to detect first, right? So can you move to the next slide? This showcase like different priority order being taken into account. Now, the problem with this particular priority order sequencing was that robot 0, when it it tries to avoid that particular collision, it will end up taking a longer path than it would have for the robot 5. So robot 5 could have taken the brunt of relocating and moving around that or like letting the robot 0 go. But because robot 0 might have the longest path, because we try to delay it even more, the total time or the total performance of the whole system will decrease. So it will take more time for the whole system to reach to its all end locations. So the priority order is again like sampled using a random forest tree or like hill climber methods. You can try different ways. I think stick with the hill climber. So you can try these random sampling methods, which will try to see, okay, which is the priority order I should go for to get the best way out for my whole system. So yeah, I think we can move to the next slide. Yeah, again, so we try to now relocate the 0, and then again there's another collision because robot 0 and robot 5 hasn't been like fully solved, etc. So yeah, so that was like just a brief of how the decoupled approach is actually happening, right? And Naman will showcase the initial few results.
Yeah, so we created a couple of cases. So 3 of the cases are shown here. CBS is conflict-based search, the algorithm we were comparing ourselves against. And you can see there are 3 scenarios that we wanted to illustrate. So the first one is a narrow corridor. Now, obviously, if there was no space for one robot to overtake, they both would not be able to plan. So even CBS or our algorithm wouldn't be able to plan, because there's no way. There could be a way of one of them reaching their goals first and then both of them moving together towards a new goal. But in that case, we are redefining what reaching a goal is. It means just touching a goal. Our definition of reaching a goal is going to that point and staying on it. The second scenario on the top right corner is what we find at a warehouse. So we call this the warehouse case. So it would be a lot of stacked shelves or some kind of product that we need to take off the shelf and move to another location. And this would be the top-down view of that. And our algorithm and CBS look very similar, like even though we do it in a much lower time than them, we get almost a 17-time improvement in certain cases. And below is a plus sign where 2 robots are entering into a corridor and each of them have to go to a different location. And this case is slightly special because both robots have to stop. So one robot stopping will help the other robot get to its goal, and this will allow the previous robot also to reach in the lowest amount of time. So what we do is we define the cost of the robot stopping as well, and we give this cost also into the algorithm. So in case the algorithm finds that by stopping just for 1 second, I can get the total cost for the entire system to be 0, we would prefer stopping for that 1 second. So this would help in scenarios, especially in warehouses, even in houses. So what we can do is, instead of modeling all of them as robots, robot 1 could just be a guess of where a human is walking. So if we see a human being and we predict, okay, they'll be taking 3 steps forward, we can always use robot 0 as our plan, and we can replan for that. And along with that, we can plan for many agents. If you can see in the top right corner, we have 4 agents. And on our landing slide, we had the Reddit logo with around 5 agents. And all of this gets planned within a few milliseconds. So Saksham will show you something that we did for this showcase.
Yeah, hopefully the audio is coming now. So yeah, so what we basically did was we took the paths which was generated for each robots, plotted in like a CSV file, and then we're using that CSV file to create pitches, and then we're passing those pitches as a MIDI input to audio software, which will create all these instrument sound notes for you. So each step of different robot is creating different pitch and different notes of sounds and instrument as well. And there's one more final, I think that, so this is like the one which we made for the Reddit. And again, this is not too many parts, but the one which you will see next is like the amazing symphony which multiple robots can create, or even there's another way of thinking of how the robots can move around and operate. And it's just a beautiful thing to see and hear. So one thing to note here is CBS on the left was the one which we compared our algorithm against. SIPP, if you would have seen during the video, there were a lot of collisions which were happening. So usually the robot turns red when that happens. And the propose and the CBS were able to plan for all the robots without colliding and almost in the same time frame, and everyone reached around the same time frame. But again, propose was able to give the solution a lot faster in terms of CBS. It's up to 17% faster. So I think we can go to the next slide.
Yeah, so these are some of the tests that we did to validate our approach. On the left, there's a gazebo environment. It shows the same narrow corridor case that we tested before. And on the right side, it's our turtle bots. So many people would have used these. This was in our lab. And the turtle bots are executing the same narrow corridor case, but in real life. So there is no slam on these systems, mainly because that's not what we wanted to show in our algorithm. So ideally, if you have used ROS, you'll know about low-level planners and high-level planners. And this would be like the high-level planner. It would give a A-star based plan. And we would use something like DWA or TEB to give the low-level controls to the robot to move. And that is why you can see that these robots are moving very discreetly in that same frame-based fashion. Each robot is given a PID tune goal. So it's given XY and it just tries to reach that new XY coordinate. So you can see that every frame is sequenced. So all the robot moves happen at the same frame time. And this kind of puts all of our things together, the server client architecture, the path planning algorithm. And so one thing is, every time you run this algorithm, there could be a different result because that was the solution that was found first. But since we have a hill climber, we will try to find the best in those few scenarios. We can also just report the first successful scenario and then in the background compute the next best. Or if this one's better, we can just update saying, okay, this is not the best solution. And what we are working on is trying to port it from Python to C++ to get a bit of bonus performance. All of this is written in ROS 1 right now, and even porting it to ROS 2 is something that we are thinking about because it has better decentralized performance. Yeah, so some of the advantages of our algorithm is here. We are 17 times faster, up to 17 times faster in most scenarios, and we are open source. It's a centralized approach, so you know where each robot is at every given point in time. We have evaluated it across many scenarios. There are benchmarks, and we have run it through most of the cases. And we have averaged 10 plus runs to get our timings out. So we know that there's nothing like we are cherry picking the best cases and using them. And it's a decoupled approach. So you don't need perfect knowledge. It's ROS integrated, so you just have to clone our workspace and you can get the same outputs that we have. And finally, we have a API that is free for third parties. So yeah, this is one of the problems that we found. Initially, when we were testing our algorithm, we found that it was taking a lot more time than CBS and SIPP. But the strange thing that we found, what we noticed, is that at every time we ran the thing, it would take consistently the same amount of long time. So CBS would change. So if we had 3 robots or 50 robots, it would change, it would scale upward. But our thing would not scale. And what we realized later is we had a lot of unnecessary imports and sleeps and print statements, which was polluting how much time we were actually taking. And so it's a good thing to remember to remove your sleep calls you added a month ago just to debug. Also, we have a repository, and only we have been starring it from our own alternate accounts. So if you guys can please star a repository, that would be great.
And just to elaborate on that sleep, Matplotlib also does the same thing. So make sure you guys remove that.
Yeah, we are open for any questions, and
well, thank you too for the presentation. It's difficult presenting these very technical, very theoretical concepts in a way that's understandable. I feel like did a reasonable job at that. Just to kind of back up and go at a higher level, could you explain to the audience who maybe hasn't looked at a lot of controller planning strategies, when would you need multi-robot planning? Like what kind of environments, when would that actually be applied? And why did you choose to develop a priority-based planner? What are the advantages of that?
Okay, I think Naman can take the first part, then I'll elaborate on the second, the priority.
Yeah, so basically when we would need this is, so the reason why we developed this is for a warehouse kind of scenario. So you have a lot of robots running around and they have different goals. So for example, if you're in Amazon and you have a bunch of packages that are coming in from India and they're going to Australia, and a bunch of packages from Germany that's going to South Africa, you want them to be sorted and shifted to their respective drop boxes. And the way we do that is using robots. And what happens is there'll be an open field in the middle and there'll be a bunch of drop boxes for each location. And so these robots have to go in, navigate through, and come out the other side. What they usually do is just try to route them along a path. So they define two straight lines, and they just stay in those lines and try to go slowly and reach their goal. But we feel like if we do this like at the same time, so all the robots are moving at the same time, we will be much faster and things will go on smoothly. And another thing that we can use this for is for path planning for multiple agents. So if you have a traffic scenario and all the cars are moving in different directions, you can just use this kind of an algorithm to move them simultaneously. So right now we think of, okay, go to a signal, stop at the signal. Just imagine that this was in every traffic signal, and the traffic signal could control all of the cars at that signal. So the traffic signal would just route all the cars through a crossroad, and no cars would stop. Everyone would be moving simultaneously and they would reach their destination. Yeah, Saksham.
Yeah, so coming to the priority base, right? Like end goal of our whole system was like collectively everyone should reach to their location or goal location in the least amount of time. So where priority base comes in help is, let's say if we stop robot A, but robot A has to go to a farther distance, we are stopping that person to not go and the other people are going in front of him. It's going to create delay for this guy to reach to its goal location. So we are trying to optimize for everyone. So we are going to allow this guy to go further. Maybe later on he has to stop because of other things. We don't care about it right now. But for now, we'll allow it to go because it has a longer path. And if we disturb its path right now, overall system's total performance will go low. So that's where the priority base comes in. And the way we have implemented is so that things can be parallelized, right? Because we want the calculation to happen as fast as possible. So we will try to parallelize. Okay, so there will be a set A. So these are the set of priority which I can test. This is the second set of priorities. This is the third set of priorities. I'll run all these simultaneously, see what the end goal of performance is for each set of these priorities, and then compare them. Okay, which was better. So now here you are instead of you making use of one core of your CPU, you're able to parallelize your problem statement. And that helps to save time to calculate complex parts. So the cases which you saw are still relatively simple. As and more you increase the size of the map and you increase the number of agents, that thing becomes complex. So this is where those two things come into clutch.
Yeah, if I could add on to Saksham, each of these algorithms is like a greedy algorithm. So if it sees one location that's empty, it'll try to go to that immediately. And the only way we can give them different identities is that giving them priorities. So each of them has a priority and say, okay, first we plan for robot 1, we let him reach, and then we plan for the others. So this could also be used in some scenario where you want priority for some, okay, it's a medical robot and it needs to reach its goal first, and the other robots can reach later. We can use that and define that as priority 1. But obviously we lose that hill climbing and finding the optimal solution there.
Yeah, that makes sense. You could use it for a medical robot, or for like, if you have a person as one of your agents, they could be the priority because they're not going to move for the robot.
That's interesting. Yeah. So you guys say that your code is open source and everything. Can people use it just as a standalone ROS node?
Yeah, so right now we try to keep two things slightly separate. So the Python code is on the repository right now, whereas it's not exactly tightly integrated into the ROS node, mainly because like we wanted people who aren't into ROS to just take the code from GitHub and run it and see what is happening. We have another workspace that is linked in our GitHub repository that has the entire ROS node and everything is there in that point.
Cool. All right.
We do have a few questions from the YouTube. One question, which I think is good. When you say your algorithm is faster, are you talking about the speed, the execution time, how long the robots actually take, or are you talking about the processing, how long it takes to calculate?
Yeah, so
it's both.
Yeah,
okay. It's both. Okay, go ahead now. So it's both basically. So the execution time it takes for us to calculate these paths is less compared to the contemporary ones, which is CBS or SIPP, as well as comparatively, whatever the longest path was for which CBS was able to plan, the total performance of that whole system and our performance was equitable. And SIPP again, like sometimes failed, but that's a separate case. But yeah, so when we talk about performance or up to 17% faster, is that we are able to calculate those paths for these robots to go to 17% faster, 17 times faster than what CBS would have been able to do. Again, this is over, I think, 10 runs, which we have done. And this is also, again, spread out for 5 scenarios, 5 different maps, which we have built and tested. The more details you can find on the paper as well. But more or less, so we tested on these particular maps 10 times because, again, ours is hill climber. So sometimes it might be able to find a solution faster. So to keep things supportive and to find like what would have been the average runtime for us, we did like around 10 runs and then compared that with the CBS system.
Yeah, makes sense.
Cool. Well, I think that takes us to the end of our first session for today. So thank you guys so much for your presentation. It was really, really wonderful and interesting. And keep up the good work. Yeah, thanks for providing this to the community. It's going to be really good.
Yeah, thank you guys for like arranging all of this. I mean, we are really happy to be part of this community.
We're very happy to have you guys on, and we're really happy to organize this for the benefit of the community. So, yeah.
Thank you.
With that, of course, yeah. With that, everyone, thank you for attending the first session today on autonomous mobile robots. Please join us again in a couple hours. We're going to take actually in 1 hour, sorry. We're going to take a quick lunch break, and then we're going to be back this afternoon with our next keynote, Robotics, with their automatic recycling sorting robot. And we are going to be hearing from a lot of more professional, startup-y kind of community members. So please join us then. Thank you again, everyone, for your time.